For many years, the far side of the Moon has remained largely unknown and unexplored. Unlike the side we always see from Earth, which is covered with familiar craters and flat plains, the far side has received much less attention. Scientists have long been interested in understanding what it can tell us about the Moon's history from billions of years ago. Now, latest missions have started to study this region closely, uncovering new findings that are changing our understanding of the Moon. They have found signs of water ice, unusual types of minerals, and land formations that differ from those on the near side. The far side is proving to be an area with many unexpected and interesting features. What else might be discovered there, and why is it so important for scientists to keep studying this part of the Moon? Before we begin, comment below where in the world you're tuning in from, and what the time is there now. We're always excited about hearing where our viewers are from. The Moon is the only natural companion that moves around our planet, Earth. It travels in an orbit at an average distance of about 384,399 kilometers from us, which is roughly 30 times the width of Earth itself. The Moon completes one full journey around Earth in about 29.5 days, a period known as a lunar month. This movement is measured in relation to the Sun, and is what gives rise to the familiar phases of the Moon that we see in the night sky. Both Earth and the Moon pull on each other with their gravity, creating powerful tidal forces. These forces are what cause the daily rise and fall of the tides in Earth's oceans, and have also caused the Moon to rotate at the same speed that it moves around Earth. Because of this, the Moon always keeps the same face turned toward us, a phenomenon known as tidal locking. Scientifically, the Moon is considered a planetary mass object, meaning that while it is technically a satellite, it shares many qualities with small planets. Its mass is just a little over 1% of Earth's, and its diameter is about 3,474 kilometers, making it about 1/4 the width of our planet. This means that if you could place the Moon over the United States, it would stretch from coast to coast. Within our solar system, it stands out as being larger and heavier than any dwarf planet we know of. It is also the 5th largest and 5th most massive moon overall, but it is the biggest and most massive in comparison to the planet it orbits. The Moon's gravity is only about 1/6 of Earth's, so a person weighing 60 kilograms on Earth would weigh just 10 kilograms there. Its gravity is also about half that of Mars, making it the second strongest among all moons, surpassed only by Io, one of Jupiter's moons. The Moon is made up of different layers, much like Earth, and is considered a terrestrial body. However, it has only the faintest traces of an atmosphere, a magnetic field, and almost no liquid water. Its surface is covered with a dusty layer called regolith, made of fine particles that were thrown out when meteorites and asteroids struck the lunar crust over billions of years. The Moon's face is marked by countless craters, and some of the younger ones are surrounded by bright streaks that spread outward like rays. Long ago, the Moon was volcanically active. Streams of lava flowed mainly on the side facing Earth, where the crust is thinner. These lava flows filled ancient craters, and after cooling, formed the dark, smooth plains we now call Maria, meaning seas in Latin. These volcanic events continued until around 1,200,000,000 years ago. Scientists believe that the Moon was created about 4,510,000,000 years ago, not long after Earth formed. According to the most widely accepted theory, a Mars-sized body called Theia struck the young Earth, sending massive amounts of debris into space. This material eventually gathered together under gravity to form the Moon we see today. From Earth, the changes in the Moon's appearance over time are caused by its day and night cycle. As sunlight hits different parts of its surface, we see phases ranging from the thin crescent to the full moon. When the Moon moves through Earth's shadow, we see a lunar eclipse, when it temporarily darkens. Interestingly, the Moon appears in our sky to be about the same size as the Sun, even though the Sun is enormously larger. This perfect coincidence allows the Moon to completely cover the Sun during a total solar eclipse. The Moon shines brightly in our night sky, not because it produces its own light, but because it reflects sunlight. Despite its brightness, its surface reflects light no better than asphalt on a road. Because of the way the Moon slightly rocks back and forth as it orbits Earth, a motion called libration, about 59% of its surface can be seen from Earth over time. This means we can catch glimpses of the far side, although we never see it fully. Throughout human history, the Moon has been one of the most important celestial objects known to humankind. It has influenced our understanding of the heavens and played a central role in mythologies, religions, and artistic expressions across cultures. It has helped people measure time, guided navigation, inspired poetry, and even shaped scientific curiosity. The Moon also became the first destination beyond Earth to be explored by human-made machines. The Soviet Union launched the first successful missions in the year 1959, when Lunar 1 flew past the Moon, and Lunar 2 became the first object to crash into its surface on purpose. Later, in 1966, the Lunar 9 probe achieved the first soft landing, and Lunar 10 became the first artificial object to orbit the Moon. Human exploration reached a new level on December 24, 1968, when the American spacecraft Apollo 8 carried astronauts into lunar orbit for the first time. Just a few months later, on July 20, 1969, history was made when Apollo 11's lunar module named Eagle landed at a site called Mare Tranquillitatis, or the Sea of Tranquility. 2 astronauts, Neil Armstrong and Buzz Aldrin, walked on the Moon's surface, while their companion Michael Collins orbited above. Between 1969 and 1972, a total of 6 Apollo missions landed 12 astronauts on the Moon. They collected rocks, set up experiments, and spent as long as 3 days on the surface before returning safely to Earth. In recent years, robotic missions have returned to study the Moon once again, especially to confirm the presence of water in the form of ice hidden in its shadowed craters. These discoveries have reignited humanity's desire to go back. New plans, such as NASA's Artemis program, aim to return humans to the Moon before the end of the 2020s, with the hope of building a lasting presence there and using it as a stepping stone for future journeys deeper into space. The English name Moon, written with a capital M when referring to Earth's satellite, has a long history. It comes from the Old English word Mona, which traces back to the Proto-Germanic Menon and even further to the ancient Proto-Indo-European root mensis, meaning month. This connection between the Moon and the idea of a month shows how people long ago measured time by watching the Moon's cycles in the sky. The Latin name for the Moon is Luna, and from this comes the English word lunar. This term entered the English language through Latin, and possibly through French as well. In science and in science fiction, the Moon is sometimes called lunar to distinguish it from other moons orbiting other planets. Poets have also used the name Luna when describing the Moon as a woman or a goddess. The ancient Greeks called the Moon Selene, a name that also referred to the goddess Selene, who was seen as the embodiment of the Moon itself. The rare English adjective Selenian is sometimes used when describing the Moon as a world of its own, while the related term selenic has become associated with the element selenium in modern chemistry. The prefix seleno appears in words such as selenography, which refers to the study and mapping of the Moon's surface. In Greek mythology, Selene was later identified with Artemis, the goddess of the wilderness and the hunt. Artemis was sometimes called Cynthia because, according to myth, she was born on Mount Cynthus. The Romans later identified her with their goddess Diana, who shared many of her traits. Through language, science, and imagination, the Moon has continued to hold a special place in the human story. From its ancient myths to its modern exploration, it remains a symbol of curiosity, endurance, and discovery. A constant companion lighting Earth's night sky, while silently carrying the memory of our shared cosmic past. Isotope studies of rocks brought back from the Moon show that our natural satellite was formed about 50 million years after the birth of the solar system. Over the years, many different ideas have been proposed to explain how the Moon came into existence, but none of the early theories were able to fully explain the unusual relationship between the Earth and the Moon. One old idea suggested that the Moon was once a piece of the Earth's crust that broke away because of the planet's rapid rotation. However, for this to happen, the Earth would have needed to spin so fast that it would have been physically impossible for it to remain stable. Another idea proposed that the Moon was formed somewhere else and was later captured by the Earth's gravity. But this would have required the Earth to have an extremely large and thick atmosphere to slow down the passing Moon enough for it to be captured, something that was not possible. A third idea suggested that the Earth and the Moon formed together at the same time from the same cloud of gas and dust in the early solar system, but this also could not explain why the Moon contains fewer heavy metals than the Earth. None of these explanations could also account for the high rate of spin or angular momentum that exists in the Earth-Moon system today. The most widely accepted explanation among scientists is known as the giant impact theory. According to this theory, billions of years ago, when the solar system was still young, a massive object about the size of the planet Mars, which scientists call Theia, collided with the early Earth. This huge impact was so powerful that it sent an enormous amount of molten and vaporized rock into orbit around the Earth. Over time, this material came together and cooled, eventually forming the Moon just beyond a distance known as the Roche limit, about 2.5 times the radius of the Earth, where the planet's gravity would no longer tear the forming Moon apart. In the early solar system, such violent collisions were not rare. Computer models of these kinds of impacts have shown results that fit quite well with what we observe today. The size of the Moon's small metal core and the amount of spin shared by the Earth and the Moon. These simulations suggest that a large part of the Moon's material originally came from the impactor Theia, rather than from the Earth itself. However, more recent studies, especially those made after the year 2007, suggest that a larger portion of the Moon might have actually come from the Earth. When scientists compared samples from other bodies in the inner solar system, such as Mars and the asteroid Vesta, they found that these bodies have very different chemical fingerprints, particularly in their oxygen and tungsten isotopes, from those found on Earth. Yet, surprisingly, the Earth and the Moon share almost identical isotopic compositions. This strange similarity implies that, after the collision, the molten and vaporized materials from both Theia and the Earth might have mixed thoroughly before the Moon finally formed. However, this explanation is still being debated among scientists, as it raises further questions about how such a complete mixing could have occurred. The massive impact that created the Moon would have released an enormous amount of energy, enough to melt large parts of both the Earth's crust and the material that was thrown into orbit. This would have created what scientists call a magma ocean, a vast sea of molten rock covering both the young Earth and the forming Moon. As this molten material cooled, it gradually solidified, shaping the surface of both worlds. The Moon's magma ocean is estimated to have been hundreds of kilometers deep, possibly ranging from about 500 kilometers to more than 1,700 kilometers, before it finally cooled and hardened. Even though the giant impact theory explains many features of the Earth-Moon system, some puzzles remain. Most of the unanswered questions have to do with the exact chemical composition of the Moon. Models suggesting that a large part of the Moon came from the Earth's struggle to match the chemical data collected from lunar rocks, especially in elements like zirconium, oxygen, and silicon. A study released in the year 2022 used powerful, high-resolution computer simulations containing more than 100 million digital particles to test the impact theory in greater detail. The results of this study showed that a single, properly angled collision could immediately create a Moon-sized satellite with the right amount of iron and mass. These simulations also found that even moons that started off too close to Earth, within the Roche limit, could survive, since the intense gravitational forces would strip away some material and push them into a stable orbit farther away. On the first day of November in the year 2023, scientists published new computer studies suggesting that remnants of Theia, the ancient body that collided with Earth, might still exist deep inside our planet's mantle. If this is true, pieces of that long-lost world could still be buried beneath our feet today. After its violent birth, the newly formed Moon settled into an orbit much closer to Earth than the one we see now. From the surface of the Earth, the Moon would have looked enormous in the sky, while from the Moon, Earth would have appeared even larger. Because the two worlds were so close, eclipses would have been frequent, and the gravitational pull between them would have been extremely strong, creating much more powerful tides than those of today. Over time, this gravitational interaction, called tidal acceleration, has gradually slowed the rotation of the Earth and pushed the Moon farther away. As a result, the Moon now takes longer to orbit Earth than it once did, and its distance continues to increase very slowly each year. As the Moon cooled over billions of years, it lost most of its early atmosphere, and its surface began to take on the battered appearance we know today. Countless meteoroids and asteroids struck the lunar surface, forming craters of all sizes and ages. These impacts shaped the rugged terrain that astronauts later explored and continue to shape the Moon's surface even now. Volcanic activity on the Moon lasted for a surprisingly long time. It continued until about 1,200,000,000 years ago, covering large regions with dark volcanic rock called basalt, which forms the flat plains known as Lunar Maria. Most of this volcanic activity occurred between about 3 billion and 300 million and 3 billion and 700 million years ago, during what scientists call the Imbrian period. These lava plains are not evenly spread across the Moon's surface. Almost all of them are found on the side of the Moon that faces the Earth. The far side of the Moon, in contrast, is covered mostly by highlands and has very few Maria. Scientists are still unsure why this is the case, but one leading idea is that the Moon's crust is much thinner on the near side than on the far side. This would have made it easier for molten rock to break through to the surface and spread across the plains. It is also possible that large impacts on the near side help to weaken the crust further, allowing lava to escape more easily. The Moon's history is divided into several geological periods, each named after distinctive surface features. The oldest surfaces, found mostly outside the dark Maria, are heavily cratered. Younger regions include the Maria themselves and later craters that are less worn down. The youngest craters, such as Copernicus and Tycho, still have bright ray-like patterns of ejected material surrounding them, making them easily visible even to the naked eye from Earth. Over extremely long periods of time, the Moon will continue to move farther from Earth. In about 5 billion years, it is expected to be around 40% farther away than it is today. By that time, the Sun will also have entered its red giant phase, greatly expanding in size. If the Sun's outer layers reach the Earth-Moon system, the friction from the Sun's atmosphere might slow the Moon's orbit, drawing it back toward Earth. Eventually, the Moon could come close enough to cross within the Roche limit again, causing it to break apart under Earth's gravitational pull, scattering its remains into a ring of debris around our planet. The Moon is not a perfect sphere. Its shape is slightly stretched like a squashed ball because of the tidal pull from Earth. However, its long axis, its stretched side, is turned about 30 degrees away from directly facing our planet. This odd tilt is caused by uneven gravity across the Moon's surface, especially from ancient impact basins formed billions of years ago. The Moon's shape is also more elongated than what the present tidal forces from Earth can explain. This suggests that it solidified long ago when it orbited much closer to Earth, around half the distance it does today. Back then, the Moon was still warm and flexible, but now it has become too cold and rigid to reshape itself into perfect balance again. At present, the only significant changes in its crust are small wrinkles and ridges called Labatt thrust fault scarps, formed by slow contraction over time. When compared with other moons in our solar system, the Moon stands out as the fifth largest. By size and mass, it can be considered one of the planetary mass moons, large enough to be almost like a small planet itself. Though smaller than Mercury, it is still much larger than the biggest dwarf planet Pluto. In fact, when compared with its parent planet Earth, the Moon is the largest natural satellite in the solar system relative to its primary body. The Moon's diameter is about 3,500 kilometers, roughly 1/4 of Earth's diameter. The visible face of the Moon spans a width comparable to that of mainland Australia, or roughly equal to the size of Europe or the contiguous United States. Its total surface area covers about 38 million square kilometers, nearly as large as the combined area of North and South America. The Moon's total mass is only about 1/81st of Earth's. Even so, it is the second densest of all planetary moons, and its surface gravity is the second highest, following Io, one of Jupiter's moons. Gravity on the Moon's surface is about 1/6 of what we feel on Earth, meaning that an object weighing 60 kilograms on Earth would weigh only about 10 kilograms on the Moon. To escape its gravity completely, a spacecraft must reach a speed of about 2.5 kilometers per second, or roughly 8,600 kilometers per hour. Inside, the Moon is a layered world. It once existed in a state known as hydrostatic equilibrium, where its internal pressure and gravity were perfectly balanced, but this is no longer the case. The Moon's structure consists of a crust, a mantle, and a core, each chemically distinct. Deep within lies a solid, iron-rich inner core that may be only about 240 kilometers across. Surrounding it is a layer of liquid iron, about 300 kilometers thick. Beyond that is a partially molten boundary zone roughly 500 kilometers wide. Scientists believe that these layers formed shortly after the Moon was born, around 4.5 billion years ago, when its surface was covered by a vast ocean of molten rock known as a magma ocean. As this magma ocean slowly cooled and solidified, heavier minerals such as olivine and pyroxenes sank to form the mantle, while lighter plagioclase minerals floated upward, forming the crust. Once about 3/4 of the magma had crystallized, the remaining liquid became trapped between the crust and mantle, rich in elements that produced heat and resisted crystallization. Evidence from both chemical mapping and rock samples collected by astronauts confirms this story. Most of the crust is made of a pale rock called anorthosite, while volcanic lavas that erupted long ago reveal that the Moon's mantle is made of iron-rich minerals, even more so than those found in Earth's mantle. On average, the Moon's crust is about 50 kilometers thick. Among all moons, the Moon ranks second in density after Io. Its small inner core, no more than about 350 kilometers in radius, makes up about 1/5 of the Moon's total radius. Though its exact composition is uncertain, it probably contains mostly metallic iron mixed with small amounts of sulfur and nickel. Measurements of the Moon's slow, uneven rotation suggest that at least part of the core remains molten. The pressure at the center is estimated to be around 5 gigapascals, or roughly 49,000 times the pressure of Earth's atmosphere at sea level. The Moon's gravity is not perfectly uniform. Spacecraft orbiting it have shown that certain areas have stronger gravitational pull, known as mascons, short for mass concentrations. These mascons are found beneath large circular plains called impact basins and are caused partly by the dense lava that once filled them. However, the lava alone cannot explain all the gravitational variations, and some mascons appear in regions without any visible lava plains, suggesting deeper causes within the lunar crust. The region where the Moon's gravity dominates over Earth's is called its sphere of influence. This extends about 60,000 kilometers from the Moon, less than 1/6 of the average distance between the Earth and Moon, which is around 378,000 kilometers. The area between Earth and the Moon, where their gravitational forces interact, is known as cislunar space. The Moon today has almost no magnetic field. Its external magnetic strength is less than 0.2 nanoteslas, over 100,000 times weaker than Earth's field. It no longer has a global magnetic field, but retains small regions of magnetized crust, probably created billions of years ago when its metallic core was still active and generated a magnetic dynamo. Around 4 billion years ago, the Moon's magnetic field may have been as strong as Earth's is today, but it faded away roughly 1 billion years ago as the core cooled and solidified. Some remaining magnetic spots may have formed during giant impacts, when expanding plasma clouds briefly created magnetic fields. Interestingly, the strongest magnetized regions are found opposite the sites of massive impact basins supporting this idea. For a few days each month, about 5 or 6 days, the Moon moves through Earth's long magnetic tail, known as the magnetotail. During this time, the solar wind that normally flows across the Moon is replaced by charged particles streaming from Earth's magnetic field, giving scientists valuable opportunities to study how the two worlds interact. The Moon does not have a true atmosphere like Earth's. Instead, it has what scientists call an exosphere, a very thin layer of gas that is so light it is almost the same as a vacuum. The total amount of gas in this exosphere weighs less than 10 tons in total, which is far less than the mass of even a small building on Earth. The pressure created by this thin layer is unimaginably small, only about 3 times 10 to the power of -15 of Earth's atmospheric pressure. This pressure changes depending on the time of the lunar day, as sunlight warms or cools the surface. The gases that make up this exosphere come from a few sources. Some come from outgassing, which is when gases slowly escape from the Moon's crust and interior. Others come from sputtering, a process that happens when particles from the solar wind, streams of charged particles from the Sun, hit the Moon's surface and knock atoms free. Scientists have found several elements in this thin exosphere, including sodium and potassium, which are also found in the atmospheres of Mercury and Jupiter's moon Io. They have also found helium-4 and neon, which come from the solar wind, and argon-40, radon-222, and polonium-210, which are released after being formed by radioactive decay inside the Moon's crust and mantle. Curiously, some elements that exist in the lunar soil, like oxygen, nitrogen, carbon, hydrogen, and magnesium, are not found in the exosphere, and scientists are still unsure why this is so. Water vapour has also been detected by India's Chandrayaan-1 spacecraft. It seems to vary with latitude, being most common at around 60 to 70 degrees north and south. This water vapour might come from the slow release of ice trapped in the lunar soil, which turns directly into gas when warmed by sunlight. Most of these gases do not stay around the Moon for long. Some fall back into the soil because of the moon's weak gravity, while others escape into space, either pushed away by sunlight or swept off by the solar wind's magnetic field if they become charged particles. There is also a faint and constant dust cloud that surrounds the moon. This cloud is made from tiny dust grains thrown up by the impact of particles from comets. Scientists estimate that about 5 tons of these cometary particles hit the moon every 24 hours, knocking small dust grains into the space above the surface. Each dust grain stays suspended for roughly 10 minutes, 5 minutes to rise and 5 minutes to fall back down. At any given moment, there are about 120 kilograms of this floating dust, which can reach heights of up to 100 kilometers above the surface. The Lunar Atmosphere and Dust Environment Explorer, LADY spacecraft, through its lunar dust experiment, found that the amount of dust in this cloud increases during major meteor showers like the Geminids, Quadrantids, Northern Taurids, and Omicron Centaurids, when the Earth and Moon pass through streams of comet debris. Interestingly, the dust cloud is not uniform. It is thicker near the dividing line between the Moon's day and night sides. Samples of ancient lunar magma brought back by the Apollo missions revealed that billions of years ago, the Moon once had a much thicker atmosphere. This early atmosphere existed for around 70 million years between about 3 and 4 billion years ago. It was created by gases released from powerful volcanic eruptions and was about twice as thick as the atmosphere of present-day Mars. Eventually, this atmosphere was stripped away by the solar wind and lost into space. Today, the Moon's surface is bombarded by radiation from cosmic rays, the Sun, and the resulting secondary neutron radiation. The average radiation level during the lunar daytime is about 1.369 millisieverts per day, roughly 2.5 times the level experienced on the International Space Station, between 5 and 10 times more than on a transatlantic flight, and about 200 times higher than on Earth's surface. By comparison, a journey to Mars exposes astronauts to about 1.84 millisieverts per day, and on the Martian surface the radiation drops to around 0.64 millisieverts per day, with some shielded locations having levels as low as 0.342 millisieverts. Solar radiation also charges the Moon's fine dust particles, making them lift and float above the surface. This effect makes the lunar dust extremely clingy and dangerous, as it can damage equipment and be harmful if inhaled. The Moon's axis is tilted only about 1.5 degrees compared to the plane of its orbit around the Sun, much less than Earth's tilt of about 23.5 degrees. Because of this small tilt, the Moon experiences very little change in sunlight through its seasons. It also allows certain regions near its north pole, especially the rim of the crater Peary, to remain in almost constant sunlight. These are called peaks of eternal light. Temperatures on the Moon vary dramatically depending on sunlight. In bright sunlight, the temperature can reach around 120 degrees Celsius, while in shadow it can drop as low as minus 171 degrees Celsius. Because the Moon has no atmosphere to spread heat around, temperatures change sharply between lit and shaded areas. Crater walls and valleys play an important role in trapping or reflecting sunlight, creating vast differences in local temperature. Some craters near the poles are permanently shadowed, never seeing direct sunlight. These craters of eternal darkness are among the coldest places in the entire solar system. The Lunar Reconnaissance Orbiter recorded summer temperatures in southern polar craters at about 35 Kelvin, which is minus 238 degrees Celsius, and in the northern polar crater Hermit, temperatures fell to about 26 Kelvin, or minus 247 degrees Celsius, near the winter solstice, colder even than the surface of Pluto. Covering the Moon's crust is a layer of fine, grey, powdery material called regolith. This layer was created by billions of years of meteoroid impacts that shattered and mixed the surface rocks. The upper part of the regolith, sometimes called lunar soil, is made of tiny glassy particles of silicon dioxide. It feels somewhat like dry snow, and even has a smell similar to spent gunpowder. The regolith layer is thicker in the Highlands, about 10 to 15 meters deep, and thinner in the dark, smooth plains known as Maria, where it measures only about 4 to 5 meters. Beneath the regolith lies the megaregolith, a layer of heavily fractured bedrock that extends several kilometers below the surface. With these harsh conditions, extreme temperatures, strong radiation, and a nearly airless environment, scientists believe that even the toughest bacterial spores could not survive on the Moon's surface for more than a single lunar orbit, which lasts about 29.5 Earth days. the shape and surface of the Moon have been carefully mapped using laser measurements and detailed images taken from orbiting spacecraft. One of the most impressive and gigantic features of the lunar landscape is the enormous South Pole-Aitken Basin, located on the far side of the Moon. This ancient impact crater stretches about 2,240 kilometers across, making it the largest crater on the Moon and the second largest known impact crater in the entire solar system. It is also incredibly deep, reaching about 13 kilometers below the surface. The very lowest point lies within a smaller crater inside the larger Antoniadi crater, where the ground dips to roughly 9 kilometers below the lunar average. Not far from this great basin lies the Moon's highest region, sometimes called the Selenian Summit, which rises to more than 10 kilometers above the average surface level. Scientists believe this towering area might have formed when the South Pole-Aitken Basin was created by a huge slanted impact that caused parts of the crust nearby to thicken and lift upward. Other large circular scars such as the Imbrium, Serenitatis, Chrysium, Smithy and Oriental basins also mark the Moon's surface with their deep centres and raised rims. Interestingly, the far side of the Moon is, on average, about 2 kilometers higher than the side that always faces Earth. Over the ages, the Moon's crust has continued to change, though very slowly. Scientists have discovered long, steep cliffs known as fault scarps, which suggest that the Moon has actually shrunk by about 90 meters over the last billion years. Similar patterns of shrinkage have been seen on Mercury as well. Even regions that were thought to be quiet and inactive, such as Mare Frigoris near the lunar North Pole, show signs of cracking and shifting. Since the Moon does not have tectonic plates like Earth, these changes happen because its interior is slowly cooling down, causing the outer layers to contract and split apart. In the year 2010, photos taken by NASA's Lunar Reconnaissance Orbiter revealed something extraordinary: a cave near the Sea of Tranquility, not far from where the Apollo 11 mission landed in 1969. The entrance, about 45 meters wide and up to 80 meters long, leads into what appears to be a collapsed lava tube. This was the first confirmed opening to a lunar cave. Even more fascinating is that the temperature inside remains steady at about 17 degrees Celsius, making it far more comfortable than the harsh surface outside. Such caves could one day serve as natural shelters for astronauts, protecting them from deadly radiation, micrometeorite impacts, and the extreme heat and cold of the lunar day and night. However, entering and exploring them would be risky, as cave-ins or avalanches could occur. When viewed from Earth, the most noticeable features of the Moon are its broad, dark plains called Maria, a Latin word meaning seas. Long ago, people thought these areas were filled with water, but in reality, they are vast plains of ancient lava that solidified billions of years ago. These basaltic plains contain more iron than those found on Earth, and because the Moon has no liquid water, the rocks show no signs of weathering or alteration by moisture. Most Maria formed when molten lava poured into the low-lying basins created by massive impacts, though the largest one, called Oceanus Procellarum, or the Ocean of Storms, does not seem to match any particular impact site. As the lava cooled, it contracted and formed long, winding ridges known as wrinkle ridges, which can stretch for hundreds of kilometers. Around the edges of the Maria, the lava's slow sinking created curved depressions called arcuate rills, as the heavy basalt pulled downward and cracked the surrounding crust. Beneath the surface there are also hidden seas of lava known as cryptomaria, which were later buried by material from newer impacts. These ancient layers are believed to be older than the visible Maria we can see today. Elsewhere, powerful impacts melted parts of the lunar crust, forming pools and sheets of molten rock called impact melts. These can still be distinguished from the ancient lava flows by their texture and brightness. Winding channels called sinuous rills, such as Schroeter's Valley and Rima Hadley, are thought to be ancient lava rivers or collapsed lava tunnels. They snake across the surface, branching and curving in ways that are far larger and more dramatic than anything seen in Earth's volcanic regions. Volcanic activity also shaped many of the Moon's craters. Some were filled or partly buried by lava, such as the craters Taruntius and Gassendi, while others, like Hyginus, were formed entirely by volcanic eruptions rather than impacts. These volcanic craters are smaller and more irregular, often missing the sharp rims that mark the edges of impact craters. In several places, especially on the side facing Earth, there are shield volcanoes, volcanic domes, scoria cones, and regions covered with fine, glassy ash from explosive eruptions. Most of the Maria, however, lie on the near side of the Moon, covering about 31% of that hemisphere, while only about 2% of the far side is covered in similar lava plains. This uneven distribution is probably because the Moon's near side contains more radioactive elements that generated heat deep below the surface, melting the rock and allowing lava to rise and spread. Most of the lunar lava flows took place during what scientists call the Imbrian period, between 3 1/3 and 3 3/4 billion years ago. However, some flows are younger, only about 1 1/5 billion years old, while others date back as far as 4 1/5 billion years, almost to the time when the Moon itself first formed. In the year 2006, scientists studying a small hollow on the Moon called Ina, located in the region known as Lacus Felicitatis, made a fascinating discovery. They found sharp, rough features that were surprisingly clean and free from the layer of dust that usually covers the Moon's surface. Because there was so little erosion from falling debris, these formations seemed to be extremely young, only about 2 million years old, which is very recent in the Moon's long history. This finding, together with recordings of moonquakes and the occasional release of gases, suggested that the Moon may still be somewhat active beneath its surface. Further research revealed even more surprising clues. Scientists identified around 70 irregular patches on the Moon's dark plains, known as mare, that appeared to be sites of volcanic activity less than 50 million years old. This discovery hinted that the Moon's mantle, the layer beneath its crust, might be much warmer than scientists had believed, especially on the side facing Earth. This side of the Moon is richer in radioactive elements, which give off heat as they decay, keeping the deep crust relatively warm. In addition, evidence was found inside the Great Oriental Basin, particularly within the crater named Lowell, showing signs of basaltic volcanic activity that occurred between 2 and 10 million years ago. This suggests that some parts of the Moon, especially on its far side, may have remained geologically active for a very long time. Scientists think this could be due to a combination of an originally hotter mantle and certain areas that contained more heat-producing elements than others, which helped to keep volcanic activity going long after the rest of the Moon had cooled. The brighter areas of the Moon, called terrae or highlands, stand higher than most of the dark Maria. These highlands have been dated to about 4 billion and 400 million years old, making them some of the oldest surfaces in the solar system. They are believed to have formed from plagioclase minerals that floated to the surface when the Moon was still covered by a vast ocean of molten rock. Unlike Earth, the Moon does not have large mountains formed by the movement of tectonic plates, since it lacks the geological activity that constantly reshapes Earth's surface. Most of the Maria, those wide, dark plains, are found on the side of the Moon facing Earth. This uneven distribution may be due to the Moon's far side having a much thicker crust, which made it harder for lava to reach the surface there. One interesting theory suggests that this difference could have been caused by a slow, low-speed collision with a smaller second moon of Earth, which merged with the larger one only tens of millions of years after the Moon first formed. Another explanation is that when the Moon was much closer to Earth, the gravitational pull between them caused uneven heating inside the Moon, making the near side warmer and more prone to volcanic activity. Over the ages, one major force has continuously shaped the Moon's surface: impact cratering. Countless asteroids and comets have struck the Moon, leaving behind an extraordinary record of impacts. Scientists estimate that there are about 300,000 craters larger than 1 kilometre wide on the near side alone. These craters come in various shapes and sizes. The smaller ones are simple bowls with raised rims, while larger ones have flat floors, stepped walls, and even peaks in their centres. The biggest impacts form structures with multiple rings of mountains, called multi-ring basins. While most lunar craters are round, some have more angular or stretched shapes. Craters such as Cantor and Janssen have polygon-like outlines, likely guided by underground cracks in the crust, while others, like the Messier pair, Schiller, and Danielle, are elongated. Such shapes may result from objects striking the Moon at shallow angles, from the breakup of a single asteroid into fragments before impact, or from clusters of smaller secondary impacts caused by debris ejected from earlier collisions. Scientists use the number and size of craters to estimate the ages of different lunar regions. Because the Moon has no atmosphere, weather, or major erosion, its craters remain well preserved. The largest impact basins, like Nectaris, Imbrium, and Oriental, each hundreds or even thousands of kilometers across, serve as reference points for measuring the ages of surrounding areas. Since impacts have occurred at a fairly steady rate over time, counting craters can give a good idea of how long a surface has been exposed. However, caution is needed, because some smaller craters are not primary impacts at all. They are secondary craters formed by debris thrown far away from major collisions. These secondary craters can sometimes mislead scientists into thinking a surface is older or younger than it really is. Rocks collected during the Apollo missions, which melted during massive impacts, have been dated to between 3 billion and 800 million and 4 billion and 100 million years old. This evidence supports the idea that the Moon once went through a period of intense bombardment by asteroids, known as the Late Heavy Bombardment, when the solar system was still young and chaotic. In the 2010s, high-resolution images taken by NASA's Lunar Reconnaissance Orbiter revealed that new craters are forming on the Moon at a much faster rate than earlier estimates suggested. These studies showed that secondary cratering caused by distant ejecta from impacts stirs up the upper 2 centimeters of lunar soil roughly every 81,000 years. This is about 100 times faster than the rate previously calculated from models that only considered direct impacts from micrometeorites. Across the silent plains and rugged craters of the Moon, there exist strange and beautiful patterns known as lunar swirls. These mysterious markings shine more brightly than the surrounding terrain, their pale surfaces twisting and curling in graceful winding shapes. They seem young, almost untouched by time, as if the usual darkening caused by cosmic dust and radiation has somehow passed them by. Between these bright swirls are darker paths of soil that weave and bend like rivers of shadow, emphasizing the elegance of their forms. Many of these swirls appear in regions where the Moon's magnetic field is unusually strong, and quite a few are found directly opposite the sites of great impact craters, as though the force of those ancient collisions left invisible imprints on the far side. Among the most famous of these swirls are the Rhina Gamma formation and the bright patterns seen in Marangini. Scientists believe that these glowing patches may have been shielded, at least partially, from the constant bombardment of the solar wind, which would explain why their surfaces have weathered far more slowly than other lunar regions. Unlike Earth, the Moon cannot hold liquid water upon its surface. Any water exposed to the sun's harsh radiation quickly breaks apart into hydrogen and oxygen through a process called photodissociation, and the fragments drift away into space. Yet, ever since the 1960s, scientists have suspected that frozen water might still exist on the Moon. They proposed that icy material from colliding comets or chemical reactions between hydrogen from the solar wind and oxygen in lunar rocks could leave traces of water frozen in the deep, dark shadows of craters near the poles. Some computer models suggest that nearly 14,000 square kilometers of the Moon's surface, about 5,400 square miles, may remain in permanent darkness, where sunlight has never reached. If usable amounts of water ice are truly present there, it could one day make human settlement on the Moon far more practical, as transporting water from Earth would be incredibly costly. Over the years, many discoveries have strengthened the evidence for water on the Moon. In the year 1994, an experiment aboard the Clementine spacecraft hinted at the existence of small frozen pockets beneath the surface. Later radar studies from the Arecibo Observatory, however, suggested that what was seen might instead have been bright reflections from rocks thrown out by recent impacts. In 1998, the Lunar Prospector spacecraft used a neutron spectrometer to detect unusually high levels of hydrogen in the top layer of lunar soil near the poles, suggesting the presence of water. Even samples brought back to Earth by Apollo 15 revealed tiny droplets of water trapped inside ancient volcanic glass beads, preserved deep within the rock for billions of years. Then, in the year 2008, India's Chandrayaan-1 spacecraft confirmed the presence of water ice on the Moon's surface. Its moon mineralogy mapper detected the telltale spectral fingerprints of hydroxyl molecules reflecting sunlight, revealing that the lunar soil held far more water than previously believed, possibly up to 1,000 parts per million. 10 years later, in 2018, careful analysis of light reflected from the permanently shadowed regions near both poles confirmed the presence of frozen water within 20 degrees of the lunar poles. In 2009, NASA's L-CROSS mission sent a large impactor weighing about 2,300 kilograms into one of these eternally dark craters. Instruments studying the resulting plume of debris detected around 100 kilograms of water vapor and ice, and later, more precise analysis showed that the actual amount might have been closer to 155 kilograms, a remarkable discovery that changed our understanding of the Moon's potential resources. Further studies continued to reveal astonishing details. In May of the year 2011, scientists announced the discovery of significant amounts of water, between 615 and 1,400 parts per million, within tiny melt inclusions trapped inside a volcanic soil sample known as orange glass, collected during the Apollo 17 mission in 1972. These droplets had formed during fiery volcanic eruptions about 3.7 billion years ago, suggesting that the Moon's interior once held as much water as the upper mantle of Earth. However, this did not mean that the water was easily reachable, for these inclusions had come from deep beneath the surface and were so small that it took 39 years of advanced technology to identify them. Then, in August of the year 2018, new analysis of data from the Moon Mineralogy Mapper provided the first undeniable evidence of water ice on the lunar surface. The distinctive reflections could only have been caused by true ice, not dust or other shiny materials. These icy deposits were discovered at both poles, though they were far more plentiful in the southern hemisphere, where countless craters and crevices remain locked in perpetual shadow. Within these cold, dark traps, the ice has survived untouched for countless ages, hidden safely from the burning rays of the sun. In October of the year 2020, astronomers made yet another breakthrough. Using several different spacecraft, including the Stratospheric Observatory, for infrared astronomy, known as SOFIA, they detected genuine molecules of water on the Moon's sunlit surface, proving that even in the light of day, our nearest celestial neighbour holds far more secrets and complexity than we ever imagined. The Earth and the Moon together form what scientists call the Earth-Moon system. These two worlds are linked by their shared centre of gravity, known as the barycenter. Interestingly, this point does not lie exactly at the centre of the Earth, but deep beneath its surface, around 1,700 kilometres or about 1,100 miles down. That is roughly 1/4 of Earth's total radius, showing just how much the Moon's gravity influences our planet. The Moon does not travel around Earth in a perfect circle, but in a slightly stretched path, known as an elliptical orbit. The shape of this path is defined by something called orbital eccentricity, which for the Moon is around 0.055, a small but noticeable deviation from a circle. On average, the Moon stays about 400,000 kilometres, or 250,000 miles, away from Earth, a distance equal to roughly going around our planet 9.5 times. This enormous span of space between us and the Moon means that light takes about 1.25 seconds to travel from the Moon to Earth. The Moon takes about 27 1/3 days to make one complete journey around Earth, when measured against the background of distant stars. But because Earth and the Moon are also moving together around the Sun, it takes a little longer, about 29.5 days, for the Moon to return to the same phase we see from Earth, such as from full moon to full moon. This slightly longer cycle is known as the lunar month or synodic month, and it also happens to match the length of one full day on the Moon, from one sunrise to the next. One of the most fascinating features of the Moon's motion is that it always keeps the same face turned toward Earth. This happens because the Moon's rotation and its orbit around Earth are synchronized in what scientists call a tidal lock, or a 1-to-1 spin-orbit resonance. It means the Moon spins once on its axis in exactly the same time it takes to go around Earth. However, the Moon's movement is not entirely rigid. Because of a slight wobble in its orbit known as libration, we can actually see about 59% of the Moon's surface over time, rather than just one exact half. Unlike the moons of most other planets, the Moon's orbit is not aligned with Earth's equator, but is instead tilted closer to the flat plane of the solar system, the same plane along which the planets orbit the Sun. The Sun's gravity and Earth's pull together cause subtle shifts in the Moon's path. One of these slow changes is the rotation of the Moon's orbital plane, which takes about 18 3/5 years to complete a full turn. These complex interwoven motions of the Moon follow mathematical rules known as Cassini's laws. The gravitational pull between Earth, the Moon, and the Sun creates noticeable effects known as tidal forces. These forces cause the familiar rise and fall of sea levels, the ocean tides, but they also influence the solid ground of both worlds. Even the Moon's crust experiences gentle tides, rising and falling by about 10 centimeters, or 4 inches, during each 27-day cycle. These lunar tides have several parts: a steady one caused by Earth's constant pull, a changing one caused by the Moon's slightly elliptical orbit, and a smaller variation influenced by the Sun. Scientists have recently suggested that the Moon's steady gravitational tug may even help sustain Earth's magnetic field, which protects life from harmful solar radiation. Over time, these tidal forces create tiny but constant stresses inside the Moon's crust, occasionally causing what are known as moonquakes. These tremors are much weaker than earthquakes, yet they can last up to an hour because the Moon's dry, fractured surface allows the vibrations to echo for a long time. The existence of moonquakes was a surprise to scientists and was first detected by seismometers left on the lunar surface by Apollo astronauts between the years 1969 and 1972. On Earth, the most obvious result of tidal forces is the regular rising and falling of the oceans. Although the Moon has the strongest influence on tides, the Sun also plays a major part, up to about 40% of the Moon's effect. When the gravitational forces of the Sun and Moon combine, we experience higher than usual tides known as spring tides. When they partially cancel each other out, lower tides occur, called neap tides. Essentially, tides form two bulges in the Earth's oceans, one facing the Moon and the other directly opposite. As Earth spins, these bulges move around the planet, creating high and low tides. The bulge on the side closest to the Moon happens because the Moon's gravity pulls more strongly on nearby water. The bulge on the far side occurs because Earth itself is pulled slightly toward the Moon, leaving the distant water behind. This produces two high tides and two low tides roughly every 24 hours. However, since the Moon moves a bit each day in its orbit, the timing between high tides is about 12 hours and 25 minutes. If Earth were entirely covered by ocean with no continents, the tides would be simple and predictable, rising and falling by about 1 meter. But the real world is far more complex. The presence of continents, the friction of water moving against the ocean floor, and the shapes and depths of different sea basins all distort the rhythm of the tides. Water sloshes back and forth between oceans, creating patterns that vary from place to place. As a result, while scientists can explain tides with precise mathematics, predicting their exact timing and strength at any given spot on Earth depends heavily on careful observation and local geography. Over long ages, the tides of both the oceans and the solid body of the Earth do not rise and fall at exactly the same time as the position of the Moon. These small delays create a twisting force, or torque, that works against the Earth's rotation. This steady resistance acts like a brake, slowly draining the planet's rotational energy and angular momentum. As a result, Earth's spin gradually slows down, and part of this lost momentum is passed on to the Moon through a process called tidal acceleration. This exchange of energy pushes the Moon farther away from Earth and at the same time slightly reduces the speed of its orbit. Billions of years ago, the Moon orbited much closer to our planet, and a lunar month, the time between one perigee and the next, lasted only about 20 days. Today, after more than 3 billion and 200 million years of this gradual change, a lunar month has lengthened to about 27.5 days. This means that the Earth and the Moon are very slowly drifting apart, and as a consequence, Earth's days are growing a little longer. Thanks to the precise laser reflectors left on the Moon's surface by the Apollo astronauts, scientists have been able to measure this drift with astonishing accuracy. These laser ranging experiments have shown that the Moon is moving away from Earth by about 38 millimeters, or roughly 1.5 inches, each year. That is nearly the same rate at which human fingernails grow. At the same time, highly sensitive atomic clocks on Earth have revealed that each day becomes about 17 microseconds longer every year. Although this change is extremely small, it adds up over vast stretches of time, slowly altering the rhythm of Earth's rotation and forcing scientists to adjust coordinated universal time with leap seconds every so often. This tidal interaction between the two worlds continues to work toward a kind of balance. Eventually it will make Earth's rotation period and the Moon's orbital period perfectly match, a condition called tidal locking. The lighter body of a pair always becomes locked first, which is why the Moon already always shows the same face to Earth. But far in the future, in about 50 billion years, Earth itself would also become tidally locked, always turning the same side toward the Moon. If that ever happened, a single hemisphere of Earth would forever see the Moon in the same spot in the sky, while the other half would never see it at all. However, this distant future will never come to pass because long before that, billions of years earlier, the Sun will expand into a red giant, most likely swallowing or scorching both Earth and the Moon. If, by some extraordinary chance, the Earth-Moon system survived the Sun's fiery expansion, the friction from the Sun's extended atmosphere could still slow the Moon's orbit, causing it to spiral inward. Once it came within about 18,470 kilometers, or around 11,480 miles, of Earth, it would cross a critical point known as the Roche limit. At that distance, the tidal forces from Earth would become so strong that the Moon could no longer hold itself together. It would be torn apart, forming a beautiful but short-lived ring system around our planet. Eventually, much of that debris would fall back to Earth, leaving the planet without its Moon. From our vantage point on Earth, the Moon's appearance changes not only with its phases, but also with where we are standing on the globe and the time of year. Depending on the season and the observer's location, the Moon reaches its highest point in the sky at different times of the day and night. Interestingly, it appears highest in the winter skies and lowest in the summer, a pattern that mirrors the Sun's opposite behaviour in each hemisphere. At the North and South poles, the Moon remains above the horizon for about 2 weeks every month, just as the Sun does during the long polar days of summer. In the Arctic, tiny organisms like zooplankton even use the faint glow of moonlight to navigate the dark seas during the endless polar night. The Moon's orientation also changes depending on the viewer's position. To observers in the northern hemisphere, it appears right side up, while to those in the southern hemisphere it looks upside down. Sometimes, especially near the tropics, the crescent moon's horns point upward rather than sideways. This curious sight, known as a wet moon, gives the impression of a bowl that could hold water, and it happens when the Moon's path is steep compared to the horizon. The Moon's distance from Earth varies over the course of each orbit, from about 356,400 kilometers at its closest point, called perigee, to roughly 406,700 kilometers at its farthest, called apogee. This difference makes its apparent size in the sky fluctuate by as much as 14%. On average, the Moon's angular size is about half a degree, almost exactly the same as the Sun's, allowing the two to create perfect solar eclipses. Yet even this appearance is affected by the human mind. When the Moon is near the horizon, our brains make it seem larger than it truly is, a psychological trick known as the moon illusion. Because the Moon's rotation is tidally locked, it always keeps nearly the same face turned toward Earth. The side we see is called the near side, while the other, hidden hemisphere, is known as the far side. Although often referred to as the dark side, the far side receives just as much sunlight as the near side. It simply faces away from us. Over a full lunar cycle of about 29.5 Earth days, each side experiences day and night in turn. In the distant past, the Moon once spun much faster on its axis, but the gravitational pull of Earth raised tides on its solid surface, and the friction caused by these distortions gradually slowed its rotation until it became locked in its current state. The energy lost in this process was transformed into heat, and eventually the Moon stopped rotating relative to Earth. Interestingly, in the year 1998 and 1999, data from NASA's Lunar Prospector mission revealed two hydrogen-rich areas on opposite sides of the Moon, likely remnants of ancient water ice. Scientists believe these could have been the Moon's original poles billions of years ago, before it became tidally locked to Earth, forever showing one face to its home planet. As the Moon travels around the Earth, it also spins slowly on its own axis, always keeping the same face turned toward our planet. This slow rotation creates what we call a lunar day, which lasts as long as one lunar month, about 29.5 Earth days. The reason for this is that the Moon is tidally locked to the Earth, meaning its rotation and orbit are perfectly balanced. However, the Moon is not tidally locked to the Sun, so every part of it experiences both daylight and night time as it moves through space. From Earth, the gradual change in the way sunlight falls on the Moon creates the familiar lunar phases, from the slender crescent that grows, the waxing crescent, to the full round disk, and then back to the thinning, waning crescent, which marks the Moon's sunset phase. The far side of the Moon, which never faces Earth, experiences the darkest nights, especially during lunar eclipses. The near side, on the other hand, is gently lit even during its night by a glow called Earthshine, sunlight reflected off Earth's clouds and oceans. This soft light is bright enough for an observer on Earth to faintly see the Moon's surface features even when the Sun is not shining on them. During these times, the moon's night is about 43 times brighter, and sometimes even 55 times brighter, than a completely dark, moonless night on Earth. The moon does not orbit the Earth in a perfect circle, but in an elongated or elliptical path. Because of this, its distance from Earth constantly changes. When it comes closest, a point called perigee, the moon is roughly 14% nearer to Earth than when it is farthest away, at apogee. As a result, its apparent size in the sky can look up to 30% larger, and its brightness can vary by about the same amount. A full or new moon that occurs near perigee appears especially big and bright, earning the popular name supermoon. For centuries, astronomers have debated whether the moon's surface changes over time. Some observers once believed they saw shifting spots or new formations. Today, most scientists agree that these reports were illusions caused by changing light conditions, imperfect instruments, or atmospheric distortion. Still, occasional gas releases, known as outgassing events, do happen and may explain some of the mysterious brief flashes or glows known as lunar transient phenomena. Recent studies suggest that about 1 million years ago, a region roughly 3 kilometers wide on the moon's surface may have been altered by such a release of gas. The moon's brightness and colour come from the way its surface reflects sunlight. Its overall reflectivity, or albedo, is only about 12%, similar to the dull grey of old asphalt. This means that despite appearing bright in the night sky, the moon is actually quite dark. Its surface is covered in a blanket of fine rock dust called regolith, created by billions of years of meteorite impacts. When sunlight hits this powdery surface, it scatters in all directions, making the moon look especially bright at full phase. Without the influence of Earth's atmosphere, the moon's true colour is a soft brownish grey. The dark regions, called Maria, Latin for seas, are ancient lava plains rich in iron and titanium, giving them a darker hue. The lighter highlands are made mostly of feldspar, a pale mineral. When viewed from Earth, our atmosphere can change the moon's apparent colour. It may appear deep red during a lunar eclipse, when sunlight is filtered through Earth's atmosphere, or bluish if the air is filled with fine volcanic dust. Because of this, people often speak of blood moons and blue moons, although the names are sometimes used to describe particular full moons in the calendar year rather than their actual colours. The moon also has a special way of reflecting light called retroreflection, which means it tends to scatter light back toward its source. This gives the moon a steady, even glow across its disk without much shading at the edges. Its brightness and apparent size still change as it moves closer or farther from Earth, reaching up to 30% more brightness and appearing about 14% larger when at perigee. Again, the moment of a supermoon. Eclipses occur when the Sun, Earth and Moon align in a straight line, a configuration called syzygy. When the Moon passes between Earth and the Sun during a new moon, it causes a solar eclipse. When Earth moves between the Sun and the Moon at full moon, we see a lunar eclipse. Remarkably, the Sun and the Moon appear nearly the same size in Earth's sky, about half a degree wide, because the Sun, though vastly larger, is also much farther away. This delicate balance allows both total solar eclipses, when the Moon completely covers the Sun, and annular eclipses, when the Sun forms a fiery ring around the smaller appearing Moon. Over vast stretches of time, these eclipses are changing. The Moon is slowly drifting away from Earth by a few centimeters each year, causing its apparent size to shrink. Meanwhile, the Sun is gradually expanding as it ages. Hundreds of millions of years ago, the Moon always covered the Sun completely during eclipses, but hundreds of millions of years in the future, it will appear too small to do so, and total solar eclipses will no longer occur. Only annular ones will remain. Eclipses do not happen every month because the Moon's orbit is tilted by about 5 degrees compared to Earth's orbit around the Sun. They only occur when the Moon crosses the plane of Earth's orbit at just the right time, near one of the 2 points where the orbital paths intersect. These patterns repeat in cycles called saros, lasting about 18 years. Another fascinating phenomenon connected to the Moon is occultation. As the Moon moves across the sky, it occasionally passes directly in front of a bright star or planet, temporarily hiding it from view. In fact, a solar eclipse is simply an occultation of the Sun. Because the Moon is relatively close to Earth, these events are not visible everywhere at once, and different stars are occulted each year due to the slow wobble or precession of the Moon's orbit. The moon illusion is a fascinating trick of the eyes that makes the Moon look much larger, when it is close to the horizon than when it is high in the sky. People have noticed this strange effect since ancient times, and it has been recorded by many different cultures around the world. Even tens of thousands of years ago, humans were already paying close attention to the moon. Some of the oldest cave paintings, dating back about 40,000 years, might have been inspired by its phases. Other ancient objects, such as tally sticks made between 20,000 and 30,000 years ago, may have been used to track the moon's changing shape, the waxing and waning that repeat in a steady rhythm each month. Early people likely used these patterns to keep track of time, marking the passage of days and seasons by the moon's light. Over the centuries, the moon became more than a bright light in the sky. It became a symbol and a sacred presence. In many ancient societies, it was represented by gods and goddesses. These lunar deities appeared in myths, stories, and the earliest writings from the 4th millennium before Christ. One of the oldest known depictions of the moon is carved into a stone in North Ireland, around the year 3000 before Christ. Around the same era, people in Mesopotamia also portrayed the moon as a crescent associated with the lunar god Nana, also known as Sin. Among the earliest astronomers was a remarkable woman named Enheduanna, who lived in ancient Akkad. She was both a high priestess and a poet, serving the lunar god Nana, and was the daughter of the famous ruler Sargon the Great, who reigned from about 2334 to 2279 before Christ. Enheduanna kept careful watch of the moon's movements from her temple chambers, continuing a deep tradition of celestial observation. By around 1800 to 1600 before Christ, humans began recording the moon's place among the stars. A stunning artifact called the Nebra sky disk from Germany shows the moon alongside other celestial objects, such as the Pleiades star cluster. This is considered one of the earliest known astronomical maps ever made. In ancient Greece, philosophers sought to understand the moon's true nature, and Anaxagoras, who lived until 428 before Christ, suggested that both the sun and the moon were great spherical rocks, and that the moon shone not by its own light, but by reflecting the sun's rays. Around the same time, Babylonian astronomers recorded the Saros cycle, an 18-year pattern of lunar eclipses, while Indian astronomers studied how the moon's position changed over each month. In China, the astronomer Shi Shen taught how to predict solar and lunar eclipses with careful observations of the heavens. The great philosopher Aristotle, who lived from 384 to 322 before Christ, believed the moon formed a boundary between the ever-changing world of Earth and the perfect eternal realm of the stars. His ideas shaped how people saw the universe for centuries. Around the same era, Archimedes built a kind of mechanical planetarium that could calculate the movements of the moon and other planets. In the 2nd century before Christ, Seleucus of Seleucia correctly suggested that ocean tides were caused by the moon's pull and that their strength depended on its position relative to the sun. Another Greek thinker, Aristarchus, even estimated the moon's distance from Earth, guessing it to be about 20 times Earth's radius, not far from the truth. In ancient China, during the Han Dynasty, scholars believed that the moon's glow came from reflected sunlight. The philosopher Jing Fang, who lived between 78 and 37 before Christ, correctly described the moon as a sphere. Later, the astronomer Ptolemy, born around 90 and living until 168 after Christ, made careful measurements, calculating the moon's distance to be about 59 times Earth's radius, and its diameter to be about 29% of Earth's, very close to modern values. Around this same time, the writer Lucian imagined a voyage to the moon in his playful story A True Story, where travellers meet lunar inhabitants, one of the earliest works of science fiction. A few centuries later, in the year 510 after Christ, the Indian astronomer Aryabhata explained that the moon's brightness came from sunlight reflected off its surface. Centuries later, the brilliant Arab scientist Ibn al-Haytham, who lived from 965 to 1039, studied how light behaved on the moon. He discovered that the moon did not reflect light like a mirror, but scattered it from every part of its bright side. Around the same time in China, the Song dynasty scholar Shen Kuo compared the changing shapes of the moon to a round ball of silver, bright in full light, crescent-shaped when seen from the side. During the Middle Ages, even before telescopes were invented, scholars came to accept that the moon was spherical, though many still imagined it to be perfectly smooth. Then, in the year 1608, the telescope was developed, opening a new era of discovery. The Englishman Thomas Harriot made the first telescopic drawings of the moon in the summer of 1609, but he did not publish them. Around the same time, Galileo Galilei also began using telescopes to study the sky. In 1610, he published his revolutionary book Sidereus Nuncius, showing that the moon had mountains and craters, shattering the belief that heavenly bodies were flawless. Later in the 17th century, Giovanni Battista Riccioli and Francesco Maria Grimaldi created the system of naming lunar features that is still in use today. In the early 19th century, Wilhelm Beer and Johann Heinrich von Mädler produced the most accurate lunar maps yet, between 1834 and 1836, and published De Monde in 1837. Their studies measured the heights of over 1,000 mountains on the moon and marked the beginning of modern lunar geography. At first, scientists believed the moon's craters were volcanoes, but in the 1870s, Richard Proctor proposed that they were caused by impacts. His idea gained support in the late 19th century and was confirmed by experiments in the 20th. By the 1950s, the study of the moon's surface had grown into a full scientific field known as lunar stratigraphy, the study of its layers and history. After the Second World War, powerful rockets were developed, and by the end of the 1950s, both the Soviet Union and the United States had the ability to launch spacecraft into space. Their rivalry, known as the Cold War, sparked the dramatic space race, which eventually became the Moon Race, a race to explore and land on the moon. In 1957, during the International Geophysical Year, the Soviet Union launched Sputnik 1, the first artificial satellite. Soon after, their lunar program achieved many firsts. In January of 1959, Lunar 1 became the first spacecraft to escape Earth's gravity and pass near the moon. Later that same year, Lunar 2 became the first object to impact the lunar surface, and Lunar 3 took the first photographs of the moon's far side. In 1966, Lunar 9 made the first soft landing, and Lunar 10 became the first spacecraft to orbit the moon. In 1961, American President John Fitzgerald Kennedy promised that the United States would land a man on the moon before the decade ended. NASA began sending robotic missions, Ranger, Lunar Orbiter, and Surveyor, to study the lunar surface. These missions prepared the way for the Apollo program, which carried humans to the moon. In December of 1968, Apollo 8 became the first crewed spacecraft to orbit the moon, following earlier animal missions such as Zond 5, which carried 2 tortoises around the moon. Then came the historic moment. On July 21, 1969, at 2:56 in the morning Universal Time, Neil Armstrong became the first human to set foot on the moon during the Apollo 11 mission. His words, "That's one small step for man, one giant leap for mankind," were broadcast to about 500 million people, the largest live audience in history at that time. Between Apollo 11 and Apollo 17, except Apollo 13, which had to turn back, astronauts collected 380 kilograms of lunar rocks and soil in over 2,000 separate samples. They also set up scientific instruments, seismometers, magnetometers, and heat probes that continued sending data back to Earth until 1977. Some instruments, like the laser reflectors, are still being used today. The final crewed mission to the moon, Apollo 17, took place in 1972. A year later, Explorer 49 became the last American spacecraft dedicated to lunar research until the mid-1990s. After the great successes of the 1960s, the Soviet Union continued sending robotic spacecraft to explore the moon until the year 1976. In 1970, the mission Lunar 17 delivered the first remote-controlled rover, Lunokhod-1, to the moon's surface. This small but historic vehicle became the first robot ever to roam across another world. Over the next few years, the Soviets launched 3 more robotic missions that successfully collected and returned a total of about 1/3 of a kilogram of lunar rocks and soil. These were Lunar 16 in 1970, Lunar 20 in 1972, and Lunar 24 in 1976. After that final Soviet mission in 1976, lunar exploration grew quiet for about 14 years. Human attention turned elsewhere, to the study of other planets and to the growing work in Earth's orbit. The Soviet Venera program explored Venus, while the American Pioneer 10, launched in 1972, became the first spacecraft to journey beyond the planets of the inner solar system. At the same time, both powers were building communication satellites, Earth-observing satellites such as Landsat, and the first space stations, including the Soviet Salyut series that began in 1971. In the late 1970s, the only significant event involving the Moon was political rather than scientific. In 1979, nations began negotiating the Moon Treaty, which was later ratified in 1984. After that, the Moon remained mostly untouched until the year 1990. In 1990, Japan sent a spacecraft named Highlands, carrying a smaller probe called Hagoromo, marking the first dedicated lunar mission since 1976, and the first ever lunar mission not launched by either the United States or the Soviet Union. 4 years later, in 1994, the United States returned to lunar exploration with the Clementine mission, the first American spacecraft to fly to the Moon since 1973. Clementine produced the first near-global topographic map of the Moon and the first detailed colour images covering almost the entire lunar surface. This achievement was followed in 1998 by the Lunar Prospector mission, whose instruments detected large amounts of hydrogen at the lunar poles, strong evidence suggesting the presence of frozen water buried beneath the surface. A new age of international lunar exploration began in the early 2000s. Between 2004 and 2006, the European Space Agency's Smart 1 orbited the Moon and mapped its surface composition in detail. In 2007, China launched Chang'e 1, its first lunar orbiter, which produced a complete image map of the Moon. India followed in 2008 with its Chandrayaan-1 mission and its Moon Impact probe, becoming the fifth and sixth nations to reach and impact the lunar surface. The mission revealed chemical and mineral maps of remarkable precision and confirmed the existence of water molecules in lunar soil. The United States returned once more in June of 2009, launching the Lunar Reconnaissance Orbiter, LRO, and the LCROSS impactor. LCROSS deliberately crashed into the crater Cabeus in October of that year to search for water, while LRO remained in orbit where it still operates today, mapping the Moon in exquisite detail. China continued its program with Chang'e 2 in 2010, producing high-resolution maps, and then in 2013 Chang'e 3 landed on the Moon, deploying the rover U2, also known as the Jade Rabbit. This was the first soft landing on the Moon since the Soviet Lunar 24 in 1976, and the first rover mission since Lunar 2 in 1973, making China the third nation ever to perform a lunar landing. In 2014, the Manfred Memorial Moon mission, the first privately funded lunar probe, successfully reached lunar orbit. Then, in early 2019, China achieved another historic milestone with Chang'e 4, which became the first spacecraft ever to land on the far side of the Moon. That same year, India sent its second mission, Chandrayaan-2, to continue studying the Moon's surface and composition. In 2020, China completed its first robotic sample return mission, Chang'e 5, which brought back 1,731 grams of lunar soil and rock. The first lunar samples returned to Earth in over 4 decades. Meanwhile, the United States had begun developing plans for returning astronauts to the Moon. This effort, known as the Artemis program, was officially launched in 2004 and gained international momentum in 2020 with the signing of the Artemis Accords, a cooperative framework for peaceful lunar exploration. Many countries have since joined these accords, inspired by the renewed spirit of exploration and partnership. In 2022, South Korea launched Danyuri, its first lunar mission, marking another important milestone. Then, in 2023 and 2024, India and Japan both achieved successful soft landings on the Moon, becoming the fourth and fifth nations to do so, following the Soviet Union and the United States in the 1960s and China in the 2010s. Japan's lander, the Smart Lander for Investigating Moon, SLIM, even survived 3 long lunar nights, a remarkable engineering accomplishment. In 2024, a privately built American lander, Intuitive Machines IM-1, became the first commercial spacecraft ever to land on the Moon. That same year, China launched Chang'e 6, which collected samples from the far side of the Moon, a world first, and carried a small rover for infrared surface studies. Along with it travelled Pakistan's Akube Q orbiter, marking Pakistan's debut in lunar exploration. Several other missions, including Nova C2, iSpace Lander and Blue Ghost, were also launched in that same year. Both the Artemis and Chang'e programs are now advancing toward the next great phase, building a human presence on the Moon. China and Russia have announced plans for joint lunar bases, while the United States and its partners intend to first assemble the Lunar Gateway, an orbital space station from which astronauts will descend to the surface. Unlike the brief Apollo landings of the past, the Artemis program aims to establish a lasting human foothold on the Moon. NASA is working with private companies to build advanced communication systems, including a fourth-generation 4G lunar network, planned to be tested aboard an Intuitive Machines Nova C lander in 2024. The Defense Advanced Research Projects Agency, DARPA, is also supporting lunar development by asking private industries to create a 10-year plan for using local resources and laying the foundation of a future lunar economy. In the year 1959, only a year after the dawn of the space age and the first ever orbital flight, humanity achieved something extraordinary. The first robotic probes from Earth successfully reached the Moon. This was the beginning of the Soviet Union's lunar program, marking the first step in our long journey of exploration beyond our planet. From that moment onward, humankind's fascination with the Moon only grew stronger, leading to the launch of many more robotic missions and eventually to people themselves setting foot on the lunar surface. The great milestone came in the year 1969, when humans first stayed on the Moon during the historic Apollo missions. These crewed explorations continued until 1972, leaving behind not only human footprints, but also tools, scientific instruments, and even symbols of peace and unity. Although no humans have returned to live on the Moon since then, our presence has never truly ended. The remains of landers, orbiters, and even crashed probes still rest there, silent witnesses of humanity's determination to explore the unknown. Over the decades, several orbiters and landers have continued to form a small but constant lunar infrastructure, keeping watch over the Moon and transmitting data back to Earth. Among them is NASA's Lunar Reconnaissance Orbiter, launched in the year 2009, which still circles the Moon today, mapping its surface and preparing for future missions. China's Chang'e 3 lander, launched in the year 2013, still operates its Lunar Ultraviolet Telescope, observing the stars from the Moon's quiet surface. Since the 1970s, 5 retroreflectors have also been placed on the Moon, used to measure tiny changes in its motion through precise laser beams fired from Earth. In recent years, interest in the Moon has expanded once again. As humans plan to explore more distant places, such as the Moon's far side and its icy north and south poles, there is a growing need for new lunar infrastructure. To support these missions, orbiters have been placed around the Moon, and even at the Earth-Moon Lagrange points since 2006. Some of these, like the Chinese Queqiao and Queqiao-2 relay satellites, move in special orbits that make it possible to maintain constant communication, even with spacecraft on the hidden far side of the Moon. Soon, a new space station called the Lunar Gateway, the first ever built beyond Earth, will orbit near the Moon as part of NASA's Artemis program, creating a base for long-term human presence. However, this new age of exploration also brings new concerns. Although the Moon is considered a low-risk body in terms of planetary protection, scientists and ethicists have begun to discuss how human activity could slowly damage its untouched state. The Moon's lack of atmosphere means that any dust kicked up by landings or impacts can spread widely, possibly contaminating its surface and affecting future scientific studies. Some scholars, like Alice Gorman, argue that even though the Moon is lifeless, it still has its own natural rhythms and should be treated as a living partner in exploration, a place whose balance must be respected. One famous example of how unregulated activity can cause controversy was the so-called tardigrade affair in the year 2019. When the Israeli Bereshit lander crashed on the Moon, it was later discovered that it had been carrying tiny microscopic creatures called tardigrades, raising questions about the lack of international rules to prevent biological contamination on other worlds. Another growing issue is space debris. As more nations and private companies send missions to the Moon, the amount of debris orbiting it is increasing, creating a potential hazard for future spacecraft. Scientists have also raised concerns about lunar waste management, how to responsibly deal with discarded equipment, garbage, and human remains left behind on the Moon's surface. Indeed, human remains have already been sent to the Moon by private companies such as Celestis and Elysium Space as part of so-called space burials. But this practice has faced criticism, especially from indigenous leaders who see the Moon as sacred. In 1998, for example, Then Navajo Nation President Albert Hale objected when NASA sent a small portion of astronomer Eugene Shoemaker's ashes to the Moon. Alongside such memorials, the Moon still holds several artifacts that serve as permanent reminders of human presence and creativity. Among these are the Moon Museum, a tiny ceramic plate carrying the artwork of 6 famous artists, the goodwill messages from Apollo 11, 6 commemorative plaques, and the small metal sculpture known as the Fallen Astronaut, honouring those who died in the pursuit of space exploration. The Moon has also played a vital role in astronomy and in our view of Earth itself. From the Moon's surface, Earth appears as a bright blue and white globe, about twice the width of 2 little fingers held at arm's length, 3 to 4 times larger than how the Moon or Sun appear from Earth. The first photographs of Earth taken from the Moon were captured by Lunar Orbiter 1 in 1966, but it was in 1968 that astronaut Bill Anders, aboard Apollo 8, took the legendary photograph Earthrise, which showed our planet rising above the lunar horizon, an image that profoundly changed how humanity saw itself. In April of 1972, the Apollo 16 astronauts set up the first dedicated lunar telescope, called the Far Ultraviolet Camera Shust Spectrograph, which captured many images and spectra of distant stars. Scientists have long recognized that the Moon is an excellent location for telescopes. It is close to Earth, has no atmospheric distortion, and its far side is shielded from Earth's radio interference, making it ideal for radio astronomy. Certain craters near the lunar poles are permanently shadowed and extremely cold, perfect for infrared telescopes. In fact, lunar soil could even be mixed with carbon nanotubes and epoxy to build huge mirrors, possibly up to 50 meters wide, while a simple lunar zenith telescope could be made cheaply using ionic liquid. Yet, as human activity increases, so does the movement of lunar dust, which could create thin layers of haze and interfere with astronomical observations if not carefully managed. During the Apollo era, 12 astronauts lived on the Moon, in pairs for short stays of up to 3 days each, spread across 6 missions. All of them lived inside the Apollo lunar module, their small but remarkable home on another world. They spent long hours exploring the surface, collecting rocks, and driving their lunar rovers across the dusty plains. But life on the Moon was not easy. The fine, powdery dust clung to their suits and tools, and even found its way inside their spacecraft. The astronauts said it smelled like gunpowder and gave them sore throats and sneezing fits. This so-called Apollo aroma was a constant reminder that lunar dust could be more than a nuisance. It could also pose real health risks. Even so, humanity continues to test life's limits on the Moon. In the year 2019, a tiny plant seed carried aboard China's Chang'e. 4 missions sprouted briefly inside its sealed mini-biosphere, the first living organism ever known to grow on the Moon. Though the seed soon withered, it symbolized a new chapter in humanity's connection with our closest celestial neighbor, a story that began with the first robotic probes of 1959 and continues to unfold in the new era of lunar exploration. The Moon carries on its face the marks of a violent and ancient history. Its surface is covered with an uncountable number of craters, silent witnesses to the cosmic collisions that took place billions of years ago, when the young solar system was a stormy and chaotic place. Some of these craters are so small that they look like tiny dimples, while others are enormous, stretching hundreds of miles across. But among all these scars, one stands out as truly exceptional: the South Pole-Aitken Basin, often called SPA. This gigantic structure, located on the far side of the Moon where earthly eyes cannot see it directly, is not only the largest and deepest confirmed impact basin on the Moon, but also one of the biggest and oldest known impact sites in the entire solar system. Its enormous size, mysterious position, and scientific value have made it one of the most fascinating destinations for NASA and many other space agencies. The SPA Basin is like a time capsule, holding secrets about how the Moon was formed, what lies inside it, and what kinds of catastrophic events once shook the early solar system. The discovery of the South Pole-Aitken Basin did not happen all at once. It took decades of patient work and many robotic missions before scientists fully realized what they were looking at. The first clues appeared in October of 1959, when the Soviet spacecraft Lunar 3 sent back the very first pictures of the Moon's far side. The images were blurry and grainy, but they revealed a surface that was heavily cratered, and very different from the smoother side that always faces Earth. Then, in the middle of the 1960s, NASA launched its Lunar Orbiter program, sending a series of spacecraft to orbit the Moon. These orbiters took clearer and more detailed photographs of the far side, allowing scientists to begin noticing a huge, faintly visible depression, what would later be recognized as the South Pole-Aitken Basin. The Apollo missions later added even sharper images, confirming that this mysterious feature was truly enormous. Yet even with all these photographs, the basin's full depth and structure were hard to see clearly, because the low sunlight near the lunar poles cast long, deep shadows that hid many of its features. The name of the basin tells the story of where it lies. It wraps around the Moon's south pole and stretches northward toward the Aitken crater, which sits near its upper edge. Its shape is roughly round, although slightly oval in some areas, showing that the huge object which struck the Moon did so at an angle. The sheer size of the South Pole-Aitken Basin is astonishing. It spans about 2,500 kilometers, or roughly 1,550 miles from one rim to the other. To imagine that distance, think of a journey from New York City all the way to Dallas. Its depth is equally incredible, sinking between 8 and 13 kilometers, around 5 to 8 miles, from rim to floor. In comparison, the Grand Canyon on Earth, which looks vast to us, would be like a small crack beside this lunar wound. The SPA Basin is nothing less than a colossal excavation, carved into the Moon's crust by one of the most powerful impacts ever known. Even more fascinating than its size is its age. Scientists believe that the South Pole-Aitken Basin was formed between 4.3 and 4.2 billion years ago, soon after the Moon itself came into being. That places the event during a period known as the Late Heavy Bombardment, an age when enormous numbers of asteroids and comets were smashing into the planets and moons of the inner solar system. Because of its great age and size, the SPA Basin acts as a kind of cosmic landmark, helping scientists understand not only the history of the Moon, but also the violent early years of our entire solar system. By studying it, researchers can look back into a time when young worlds were still forming and being shaped by fire and stone. NASA's efforts have played a central role in revealing the secrets of this ancient scar. Early missions gave us photographs, but later ones brought the tools needed to study its chemistry, depth, and structure in detail. In the early 1990s, as the Galileo spacecraft flew past the Moon on its way to Jupiter, it captured multi-spectral images that gave scientists a new view of the basin's surface. A few years later, in 1994, NASA's Clementine mission orbited the Moon and produced high-resolution maps and colour images, showing variations in the basin's minerals and giving clues about its unique makeup. An especially important step came in 1998 with NASA's Lunar Prospector mission. This spacecraft carried a gamma-ray spectrometer, an instrument that could detect and measure elements on the lunar surface. In the South Pole-Aitken Basin, it found unusually high amounts of iron and titanium, suggesting that the massive impact had dug deep into the Moon, possibly reaching its mantle, and pulled up material that is normally buried far below the crust. The mission also measured variations in gravity over the basin, confirming its huge size and revealing that it has a special internal structure different from most other parts of the Moon. Even greater understanding came with NASA's Lunar Reconnaissance Orbiter, or LRO, which was launched in the year 2009 and continues to operate today. Equipped with some of the most advanced instruments ever sent to the Moon, the LRO revolutionized our knowledge of the lunar surface. Its Lunar Orbiter Laser Altimeter, known as LOLA, mapped the basin's surface in astonishing detail. By firing laser pulses at the ground and measuring how long they took to bounce back, LOLA built a precise three-dimensional model of the South Pole-Aitken Basin. For the first time, scientists could see exactly how deep it went, how its edges curved, and how much material the ancient impact had blasted away. These maps provided essential data to understand how such gigantic craters are formed. The LRO also carried another vital instrument called the Diviner Lunar Radiometer experiment. This device measured how hot or cold different parts of the Moon became, helping scientists learn how lunar rocks absorb and release heat. When the Diviner's thermal maps were combined with information from other spectrometers, researchers could identify what kinds of minerals were likely present in each area. These studies showed that the floor of the South Pole-Aitken Basin is rich in iron and magnesium, materials that come from deep within the Moon's mantle. This confirmed what scientists had long suspected, that the ancient impact which created SPA was so powerful that it tore straight through the moon's crust and exposed its hidden interior. The tale of how the South Pole-Aitken Basin came into existence is one of the most dramatic and captivating stories written upon the face of the moon. According to the most widely accepted idea, this colossal basin was born from a titanic collision in the earliest ages of the solar system. An enormous asteroid, or perhaps a comet, likely hundreds of kilometers wide, came hurtling through space at an incredible speed and slammed into the young moon with unimaginable force. The energy released in that single instant would have dwarfed every explosion ever recorded in the history of our planet. Rocks were instantly vaporized, molten seas of lunar material were created, and a storm of glowing debris was blasted across the moon and even out into space. The force of the impact carved out a crater so vast that its walls could not support their own weight. They collapsed inward, creating a multi-ring structure that became one of the largest known impact basins in the entire solar system. Over the course of billions of years, however, other impacts great and small have slowly worn down the edges of this ancient scar, softening its once sharp features. One of the most remarkable effects of this enormous impact is that it left the moon's crust thinner beneath the basin floor. Scientists believe that the tremendous energy of the collision stripped away a large portion of the moon's original crust, leaving behind a thinner and slightly warmer layer below. Yet, curiously, despite this thinning, the basin does not display the wide volcanic plains, known as mare basalts, that cover much of the moon's near side. Instead, there are only a few scattered patches of volcanic deposits, far less extensive than those found in regions such as Mare Imbrium or Mare Serenitatis. This mystery has sparked lively debate among lunar scientists. Some suggest that when the impact occurred, the moon's interior was not yet ready for large-scale volcanic activity. Others believe that the rocks exposed by the impact were poor in the ingredients needed to produce lava flows, or that the molten material was too thick and sticky to spread widely across the basin floor. What makes the South Pole-Aitken Basin especially important is the possibility that it may have brought material from the moon's deep mantle up to the surface. If this is true, the basin acts like a natural window into the moon's hidden interior, a scientific treasure chest offering clues to what lies beneath its crust. Researchers are especially interested in finding untouched mantle rocks, because they could reveal what the moon is made of deep down. Minerals such as olivine and pyroxene, which are also found in Earth's mantle, would serve as powerful evidence that mantle material was indeed exposed by the ancient impact. Data from spacecraft like the Lunar reconnaissance orbiter already hint that these minerals exist within the basin, but only by returning real samples to Earth could scientists confirm it beyond doubt. Understanding the mantle is key to unlocking the moon's deeper history, its inner heat, its long-lost magnetic field, and the way its layers separated and evolved over time. The mighty collision that created the South Pole-Aitken Basin may also explain why the moon's two sides look so different. The enormous energy released and the shifting of massive amounts of material could have altered the moon's gravity and reshaped the stresses within its interior. Some models even suggest that the impact might have nudged the moon's centre of mass slightly, or changed how heat flowed through its interior. These subtle but powerful changes could explain why the moon's crust is thicker on one side and thinner on the other, and why volcanic activity was concentrated mainly on the near side. The heat from such a gigantic impact would have lasted for millions of years, continuing to influence the moon's internal evolution long after the dust had settled. The scientific importance of the South Pole-Aitken Basin cannot be overstated. It is one of the oldest and largest impact sites in the solar system, offering scientists a rare window into the violent history of planetary formation. By studying its structure and the craters scattered across its surface, researchers can better understand the period known as the Late Heavy Bombardment, an era, billions of years ago, when the inner planets were bombarded by a relentless rain of asteroids and comets. But SPE is not only a record of cosmic violence, it is also a gateway to the moon's deep secrets. Collecting samples from this region could reveal the true nature of the moon's mantle and help us understand how its interior formed and evolved. And beyond that, the basin stretches into the moon's south polar region, an area of immense interest because of the confirmed presence of water ice in craters that never see sunlight. The ice was not created by the ancient impact, but the geography of the basin has helped preserve these icy deposits in its eternally shadowed regions. Instruments aboard the Lunar Reconnaissance Orbiter, such as the Lunar Orbiter Laser Altimeter, have mapped these dark areas in extraordinary detail and confirmed that significant amounts of water ice lie hidden there. This discovery is not only scientifically thrilling, but also immensely practical. In the future, water ice could be transformed into drinking water, breathable oxygen, and even rocket fuel, making a permanent human presence on the Moon far more possible. Yet reaching and exploring this extraordinary basin is no simple task. The South Pole-Aitken Basin lies on the far side of the Moon, forever turned away from Earth. This means that any spacecraft landing there cannot send signals directly home, and must rely on relay satellites orbiting above the Moon to transmit their data. The terrain itself is rugged and dangerous, filled with steep cliffs, vast craters, and deep shadows that hide the surface in eternal darkness. Some of these shadowed regions are among the coldest known places in the entire solar system, with temperatures dropping hundreds of degrees below zero on the Fahrenheit scale. Operating machines under such extreme conditions requires some of the most advanced technology and engineering humanity has ever created. Even so, the South Pole-Aitken Basin continues to captivate scientists and space agencies across the world. In January of 2019, China's Chang'e 4 mission achieved a historic milestone by performing the first ever soft landing on the far side of the Moon. Its rover, Yutu-2, rolled onto the surface of the Von Karman crater, located within the vast South Pole-Aitken Basin. Though it was not a mission by NASA, its success demonstrated that exploration of this distant and hostile landscape was possible, and it reignited global interest in this lunar wonder. Today, both NASA and other international space agencies are preparing ambitious plans to explore the basin further, using both robotic explorers and, one day, human missions. Among their boldest goals are sample return missions that would bring back real fragments of the South Pole-Aitken Basin to Earth for study. Each rock, each grain of dust, could tell part of the Moon's long-forgotten story and reveal secrets about the early solar system itself. Every mission to this mysterious region brings humanity a little closer to understanding not only the Moon but also our own cosmic origins. The Moon's surface is like a giant storybook written in stone, carrying the marks of countless cosmic events that happened over billions of years. Every crater on its face is a frozen moment in time, a scar left behind when asteroids, comets, or smaller meteoroids smashed into it with incredible force. Unlike Earth, which is alive and constantly changing with wind, rain, flowing rivers, and restless tectonic plates that slowly erase its oldest features, the Moon is silent and still. Nothing moves to smooth out its wounds. There are no rains to wash them away, no winds to erode its sharp edges, and no volcanoes to bury its ancient marks. Because of this calm and unchanging nature, the Moon acts as a kind of cosmic time capsule, preserving a nearly complete record of the early solar system, stretching back almost 4.5 billion years to the time of its birth, yet this record is not evenly spread across its surface. One of the most fascinating discoveries made by scientists is how different the two sides of the Moon look. The side we always see from Earth, the near side, is not the same as the mysterious far side that remained hidden until the first space missions revealed it. Thanks to NASA's careful study and exploration, we now understand that these two halves of the Moon tell very different geological stories. They give scientists not only insight into how the Moon itself formed and evolved, but also clues about the violent history of the inner solar system. When we gaze at the Moon from Earth, even with the naked eye, we can already see its two main kinds of landscape. The first are the bright, rugged highlands, covered in endless craters that sparkle under the sunlight. The second are the darker, smoother plains known as Maria, a Latin word meaning seas. Early astronomers long believed these dark spots were real oceans, but later discoveries showed that they are vast plains of hardened lava. Billions of years ago, molten rock from inside the Moon poured out to fill huge impact basins, creating wide, dark surfaces that appear smoother and less cratered than their surroundings. These lava floods resurfaced large portions of the near side, covering many older craters beneath thick layers of basalt. This gave the near side a gentler look, though the bright highlands still preserve countless scars from ancient impacts. The far side of the Moon, however, tells a very different story. When the first robotic probes, later confirmed by the Apollo missions and NASA's detailed maps, sent back images, scientists were stunned. The far side was covered almost completely by rugged highlands, packed with craters of all sizes, from tiny pits to massive multi-ringed basins. Unlike the near side, there are very few Maria on the far side. It is an ancient, heavily battered landscape, where nearly every inch bears the marks of billions of years of cosmic bombardment. Where the near side shows dark plains and smoother features, the far side presents a rough and cratered wilderness, a frozen record of deep time. This striking difference between the two sides is one of the Moon's most defining features. NASA's many missions have helped explain why this difference exists. The main reason lies deep beneath the surface, in the thickness of the Moon's crust. Measurements made by spacecraft such as Lunar Prospector in the late 1990s and the Lunar Reconnaissance Orbiter, launched in the year 2009, revealed that the far side's crust is much thicker than that of the near side. On average, the crust on the far side is about 60 kilometers thick, or roughly 37 miles, while the near side's crust is only around 30 kilometers thick, about 18.5 miles. This difference has shaped everything about how the Moon evolved. A thinner crust made it easier for molten rock to reach the surface on the near side, while the thicker crust on the far side acted like a lid, trapping volcanic material below and preventing most lava from breaking through. This imbalance in crust thickness likely formed very early, perhaps when the Moon itself was born. One popular explanation, called the giant impact hypothesis, suggests that the Moon was created when a Mars-sized world collided with the young Earth. The explosion sent vast amounts of molten rock and debris into orbit, which slowly came together to form the Moon. As the molten surface cooled, it hardened unevenly. Earth's gravity, tidal forces, and uneven internal heating may have caused the crust to be thinner on the side facing Earth and thicker on the far side. This early unevenness shaped the way the Moon would look for billions of years to come. Because of this, the two sides of the Moon evolved very differently. On the near side, the thin crust allowed lava to erupt more easily, filling large craters and forming the wide Maria that give the Moon its familiar face. These lava plains covered many of the Moon's older scars, giving the near side a smoother appearance. On the far side, the thicker crust made volcanic eruptions much harder. Even when enormous impacts like the one that formed the gigantic South Pole-Aitken Basin tore into its surface, the lava beneath could not easily rise to fill them. As a result, the far side kept most of its ancient craters almost perfectly preserved. It became a vast, untouched museum of impacts, while the near side was reshaped and smoothed by ancient volcanic floods. Another important clue to the Moon's uneven history lies in its inner chemistry. NASA missions discovered that certain heat-producing radioactive elements, especially potassium, uranium and thorium, are not evenly spread throughout the Moon's crust. Instruments aboard the Lunar Prospector found that these elements are much more concentrated on the near side, in a region called the Procellarum creep terrane. The word creep comes from potassium, rare earth elements, and phosphorus. As these radioactive materials slowly decayed, they released heat, keeping the near side's interior warmer and more molten for longer periods. This extra warmth helped power the great volcanic eruptions that flooded the near side with lava. The far side, poorer in these heat-producing materials, cooled faster, leaving it colder, more solid, and far less active. This difference in internal heat was another reason why the two sides of the Moon ended up so different from each other. NASA's exploration of the Moon, over decades, gradually revealed all these secrets. The first glimpse of the far side came not from NASA, but from the Soviet Union's Lunar 3 probe in the late 1950s. However, NASA's Lunar Orbiter missions in the mid-1960s provided much sharper and more complete images. These photographs, originally intended to find safe landing sites for the Apollo missions, also revealed in stunning detail how the near and far sides differed. The pictures clearly showed that the far side was dominated by cratered highlands, with only a few scattered Maria. Later missions continued to refine our understanding. In the year 1994, NASA's Clementine spacecraft mapped the Moon's surface with a laser altimeter, measuring the exact heights and depths of its mountains, plains, and basins. These data showed that the far side's highlands are on average higher than the terrain on the near side. The Lunar Prospector, launched in 1998, went even further. It mapped the Moon's gravity field and elemental composition. It found dense regions called mascons, short for mass concentrations, beneath the large Maria of the near side caused by the heavy basaltic lava flows that filled them. The far side, lacking such lava-filled basins, had far fewer of these mascons, confirming that its underground structure was very different. The same mission's gamma-ray spectrometer also revealed the uneven spread of radioactive elements that shaped the Moon's inner heat and volcanic history. The Lunar Reconnaissance Orbiter, often called the LRO, was launched in the year 2009 and has given us the most detailed and complete look at the Moon ever achieved. Through its powerful instruments, scientists have learned more about the Moon's cratered surface and the striking differences between its two faces, the near side, which always faces Earth, and the mysterious far side, which remains hidden from our view. One of the LRO's most important tools is the Lunar Orbiter Laser Altimeter, or LOLA. This device carefully mapped the Moon's surface with extraordinary precision, creating three-dimensional models that show every hill, crater and basin in remarkable detail. With LOLA's help, scientists have been able to measure the depths and widths of craters and basins more accurately than ever before. These measurements clearly revealed that the far side of the Moon has far more impact scars than the side that faces Earth, giving us new insight into the forces that shaped it. Another major instrument aboard the spacecraft is the Lunar Reconnaissance Orbiter Camera, or LROC. This camera has captured millions of extremely sharp, high-resolution photographs of the Moon. These images reveal fine details of crater walls, the rocky debris scattered around them, and the vast fields of impact marks that cover the far side. Alongside this, the Diviner Lunar Radiometer experiment, another of the LRO's instruments, has mapped how heat moves across the Moon's surface. By studying these detailed temperature maps, scientists have gained important clues about the kinds of rocks and minerals that make up the crust, and how heat flows differently through various parts of the Moon. All these discoveries have deepened our understanding of how the Moon has changed over time. The uneven patterns of cratering between the two sides tell a complex and fascinating story, one of both violent impacts from space and slow internal changes within the Moon itself. These geological processes, powered by differences in heat deep inside, work together with the constant bombardment of asteroids and comets over billions of years to shape the Moon's surface into what we see today. The far side of the Moon, with its thicker crust and smaller amount of heat-producing materials, preserved a far older surface. This ancient landscape gives scientists a rare window into one of the most dramatic chapters in the history of the solar system, the period known as the Late Heavy Bombardment. This event, which scientists believe took place roughly between 4.1 and 3.8 billion years ago, was a time when a great wave of asteroids and comets crashed into the inner planets and their moons. Because the far side of the Moon has remained largely unchanged since then, it holds a remarkably well-preserved record of those ancient collisions. By studying its craters, scientists can test their theories about the early solar system and better understand what kinds of objects were striking the planets back then. Counting craters may seem simple, but it is one of the most powerful tools in planetary science. Surfaces with many craters are usually older, since they have been exposed to space impacts for a longer time. By comparing the heavily cratered far side with the smoother, darker plains, called Maria, on the near side, scientists can build a timeline showing which regions formed earlier and which appeared later. When these crater counts are combined with rock samples collected during the Apollo missions, whose ages were measured on Earth, scientists can create a more complete and accurate history of the Moon. This technique does not just help us understand the Moon, it also helps date the surfaces of other airless worlds, such as Mercury and Mars, where no samples have been returned yet. In this way, the Moon serves as a kind of cosmic calendar, a reference point that allows scientists to estimate the ages of surfaces all across the solar system. Studying the two different faces of the Moon also helps us piece together the larger story of the solar system's early days. By examining the size, shape, and erosion of craters on both sides, scientists can learn about the kinds of space rocks that filled the young solar system and the violent conditions that existed when the planets were still forming. Unlike Earth, whose ancient impact scars have been mostly erased by wind, rain, volcanoes, and the slow drifting of tectonic plates, the Moon has preserved its ancient wounds almost perfectly. It stands as a silent witness to a time of chaos and creation, offering a precious record of the bombardments that once struck Earth itself. Through the Moon, we can look back billions of years and glimpse the violent beginnings of our solar neighborhood. The Moon's surface is a world of striking contrasts, divided into two very different kinds of terrain. There are the dark, smooth plains known as the Maria, and the brighter, rougher regions covered in countless craters called the Highlands. The Highlands spread across most of the Moon's surface and dominate the far side, the mysterious hemisphere that never faces Earth. But these highlands are much more than mere hills and valleys. They are immense, ancient archives of time, preserving the earliest chapters of the Moon's story. Their roughness, their composition, and the endless craters that mark them all whisper tales about how the Moon was born, how its inner layers separated, and how violent the young solar system once was. For many decades, robotic probes and astronauts from NASA have explored these silent lands, gathering clues that reveal not only the Moon's origins, but also the story of how rocky worlds, like Earth, Mars and Mercury, may have come to be. The lunar highlands are among the oldest surfaces in the entire solar system, representing the first crust that ever formed on our celestial neighbour. Scientists believe that these regions were created during the Moon's infancy, within the first few 100 million years after it came into existence, around 4.5 to 4 billion years ago. In contrast, the dark plains of the Maria are much younger, having formed later, between about 3.8 and 3.2 billion years ago. The birth of the highlands is tied to a fascinating idea known as the lunar magma ocean hypothesis. According to this theory, after a giant collision between the early Earth and a Mars-sized body sent debris swirling into space, the material that became the Moon was initially a glowing molten world, a vast ocean of liquid rock. As this fiery ocean began to cool, heavier minerals slowly sank inward, forming the Moon's core and mantle, while lighter minerals, especially plagioclase feldspar, floated upward, gathering into a pale crust over millions of years. This floating layer solidified into a bright, low-density rock called an orthosite, which became the bedrock of the lunar highlands. This grand process, called differentiation, separated the Moon into distinct layers by weight, much like Earth's core, mantle and crust. Yet unlike Earth, the Moon's internal activity eventually faded, leaving behind a world frozen in time. On the far side, where volcanic activity was minimal, the highlands remain almost completely untouched, preserving the Moon's original surface as it appeared billions of years ago. What makes the lunar highlands truly extraordinary is the sheer number of impact craters that cover them. From tiny pits smaller than a coin to enormous basins hundreds of kilometers wide, the entire surface is scarred by ancient collisions. These marks tell the tale of a violent era in the solar system's early history, a period called the Late Heavy Bombardment, which took place roughly between 4.1 and 3.8 billion years ago. During that time, countless asteroids and comets battered the young planets with devastating force. Because the highlands had already formed, and have barely changed since, they record nearly every one of these cosmic blows. Over billions of years, newer craters overlapped older ones, creating a chaotic and deeply textured landscape. Eventually, the surface became so densely cratered that new impacts no longer added visible marks, but instead eroded the older ones, softening the terrain into a rugged mosaic of scars. The far side of the Moon preserves these craters especially well. Its crust is thicker, cooler, and contains fewer heat-producing elements than the near side. This meant that volcanic eruptions, which smoothed over much of the near side's surface and formed the dark Maria, were rare there. The far side's highlands remained almost entirely untouched, steadily accumulating impact scars across billions of years. Today, they stand as a frozen snapshot of the Moon's wild and chaotic youth, a fossilized landscape that shows us what the solar system once looked like. Our understanding of these highlands grew enormously through NASA's lunar missions. The Apollo astronauts who landed between the late 1960s and early 1970s brought back precious samples of lunar rocks. Many of these came from highland regions or from debris that had been blasted out of distant craters. These samples confirm that the highlands are mainly made of an orthosite, a light-coloured rock rich in plagioclase feldspar. Because it is less dense than most other minerals, it naturally floated to the top of the molten lunar ocean long ago, forming the Moon's earliest crust. Later robotic missions added even more detail. In the year 1994, the Clementine spacecraft used special cameras to analyse how different kinds of light reflected off the surface, confirming that an orthosite was widespread, especially on the far side. Then, in 1998, NASA's Lunar Prospector orbiter carried instruments that measured the chemical makeup of the surface. It revealed that the Highlands contained very little iron and titanium compared to the darker Maria, just as one would expect from regions rich in anorthosite rather than volcanic rock. In the 21st century, the Lunar Reconnaissance Orbiter, launched in the year 2009, transformed our view once again. Its Lunar Orbiter Laser Altimeter, or LOLA, mapped the Moon's surface in extraordinary detail, showing the exact heights and shapes of mountains and craters across the Highlands. Its Diviner instrument measured how the surface emitted heat, identifying minerals based on their unique thermal signatures. Meanwhile, the Lunar Reconnaissance Orbiter camera captured millions of sharp, high-resolution images, revealing that the Highland surface is not smooth bedrock but a patchwork of breccias. Rocks formed when shattered fragments fused together under the heat and pressure of impacts. This proves that the Highlands have been churned, broken, and compacted repeatedly over billions of years, a continuous record of cosmic violence written in stone. The lunar Highlands are far more than an ancient landscape. They are a key to understanding our entire solar system. Like a Rosetta Stone carved in rock and crater, they help scientists decode how the Moon formed, how its molten ocean cooled, and how its surface evolved through the ages. Their widespread anorthosite composition supports the theory that the Moon began as a molten body, slowly solidifying into layers. By carefully studying the minerals, layers, and crater patterns of these regions, scientists can reconstruct the sequence of events that shaped not just the Moon, but also other rocky worlds. Because the Highlands hold the oldest, most heavily cratered surfaces, they serve as the master timeline of the solar system's early history. By counting the craters in different regions and comparing them with absolute ages determined from Apollo samples, researchers can estimate the ages of surfaces on other planets and moons. This technique, called crater counting, allows us to date landscapes on worlds like Mercury and Mars, even when no samples have been returned. The lunar Highlands give us a rare and precious window into the early story of how planets came to be. Unlike Earth, whose ancient crust has been constantly broken down and rebuilt by the restless movement of tectonic plates, volcanic eruptions, and erosion caused by wind and water, the Moon's Highlands have remained almost unchanged for billions of years. They are like a time capsule, a natural fossil record that has kept the original face of a rocky world frozen in time. By studying these ancient, untouched regions, scientists can look back to an era when the solar system was young and wild. These rugged lands reveal how rocky planets first formed their outer crusts, how massive impacts shaped their surfaces, and how the early solar system behaved during its first few 100 million years of existence. Although the Highlands are not rich in easily reachable materials such as water ice, they hold treasures of another kind. Their unique and ancient makeup may contain minerals and elements that were created during the violent events that shaped the Moon itself. For explorers and scientists, these regions, especially those on the Moon's distant far side which never faces Earth, are of great interest. They are like untouched archives waiting to be opened. Future missions that bring back samples from these areas could provide pieces of the Moon that have remained untouched since the dawn of its creation. Such material could help answer deep questions about what the Moon was originally made of, when important events occurred in the early solar system, and how the Moon's crust formed from molten rock long ago. These priceless samples would serve as a kind of ground truth, helping scientists confirm and refine the data gathered from orbiting spacecraft that have mapped the Moon from afar. Over the years, the study of the lunar Highlands, guided by NASA and other space agencies, has completely changed how humanity sees the Moon. For a long time, people thought of it as a cold, silent, and unchanging world, but thanks to decades of exploration, from the first blurry images taken in the early days of spaceflight to the detailed maps and laser scans made by modern orbiters, and the Moon rocks carried home by the Apollo missions, we now know the truth. The Moon is not just a lifeless ball of dust. It is a world with a deep and dramatic history, one that tells of fiery beginnings, great impacts, and long ages of quiet stillness. The lunar Highlands are far more than old, battered hills. They are natural laboratories written in stone. They preserve clues about the Moon's birth from molten rock, the way it separated into layers of crust and core, and the turbulent period when the solar system was still forming. Every crater, ridge, and valley tells a story from a time when planets were being born, and space was filled with constant collisions and creation. In studying them, we are not only uncovering the Moon's own history, but also learning about how Earth and other rocky worlds in our cosmic neighbourhood came to be in those early mysterious chapters of the universe's story. For countless generations, people have watched the moon grow and shrink through its beautiful monthly cycle, from thin crescent to glowing full circle and back again. Yet despite how close and familiar it seems, a deep misunderstanding has long existed in popular culture and everyday speech. The belief that the moon has a dark side, a mysterious half that never sees the sun and remains forever hidden in shadow. This idea sounds poetic, but it is completely wrong. It comes from a simple mix-up between a side that is hidden from Earth and one that is hidden from sunlight. Thanks to many years of careful observation and exploration by NASA and other space missions, this old myth has been fully disproven. In truth, the entire moon, both the side we see and the side we cannot, goes through regular periods of day and night, just like our own planet Earth. This confusion exists because of the moon's special relationship with Earth, a condition called tidal locking. The moon is tidally locked to our planet, which means that the time it takes to spin once on its own axis is exactly the same as the time it takes to complete one full orbit around Earth. In simple terms, the moon turns on itself and circles Earth at the same rate. Because of this synchronized dance, the same side of the moon always faces our world. This is why, no matter when we look at the moon, we always see the same pattern of bright plains and dark spots. Those dark areas are the ancient volcanic plains known as Maria. The side that faces us is called the near side, while the opposite one, which always faces away from us, is known as the far side. Since we always see the same face, many people naturally assume that the far side must always be dark. But dark, in this case, does not mean without sunlight. The sun, not the Earth, provides the light that shines on the moon. As the moon orbits around our planet, and as both move together around the sun, sunlight falls on different parts of the moon's surface at different times. Just like Earth, the moon has a moving boundary called the terminator, the dividing line between the sunlit side and the shadowed side. This line slowly sweeps across the lunar surface as the moon spins and travels through space. Imagine walking in a big circle while always keeping your face turned toward the center. Your back would always point away, yet sunlight could still shine on it as you move. The moon behaves in exactly this way. Its far side always faces away from Earth, but not always away from the sun. During its orbit, sunlight reaches every part of the moon, one side after the other. A full lunar day, the time it takes for the sun to cross the moon's sky and return to the same spot, lasts about 29.5 Earth days, which is roughly 1 month. This period is known as a synodic month. During this time, each part of the moon experiences about 14 Earth days of sunlight, followed by about 14 Earth days of darkness. When the side facing Earth is having its long lunar night, the far side is glowing in full daylight. And when the side we see is shining brightly as a full moon, the far side is wrapped in night. Think of the moon's phases as seen from Earth. When there is a new moon, the moon looks dark because the side facing us is turned away from the sun. Yet at that very moment, the far side is flooded with sunlight. When there is a full moon, the near side is fully lit by the sun, while the far side is in deep shadow. As the moon moves through its familiar phases, from new to full and back again, the sunlight steadily moves across both sides. So, in one lunar month, every part of the moon gets its share of day and night. There is no side that's always dark, only sides that take turns being lit. The phrase, dark side of the moon, became popular long before people ever saw what the far side actually looked like. In English, dark can also mean unknown or hidden, not simply without light. Before the age of space exploration, the far side truly was a mystery. It was the unseen half of the moon, a blank space on maps, a place of speculation and imagination. This confusion of language, mixing unseen with unlit, is what led to the myth. It was not until the late 1950s that humans finally caught their first glimpse of the far side. In October of 1959, the Soviet spacecraft Lunar 3 became the first to photograph it. The pictures were blurry and rough, but they showed something remarkable. The far side was clearly lit by sunlight. Without sunlight, those photographs would have been impossible. Nearly a decade later, in December of 1968, NASA's Apollo 8 mission gave the first direct human proof that the far side receives sunlight. Astronauts Frank Borman, James Lovell and William Anders were the first people to orbit the moon and see its hidden face with their own eyes. As their spacecraft came around from behind the moon, they saw its far side glowing in sunlight and broadcast live images back to Earth. During that historic flight, William Anders captured the world-famous photograph Earthrise, showing our blue planet rising above the rocky sunlit surface of the Moon. The front of the picture, the Moon's far side, is brightly lit, a clear sign that it enjoys its own lunar day. Later, Apollo missions continued to confirm this truth. From Apollo 8 through Apollo 17, astronauts orbited the Moon many times, passing repeatedly over the far side. They took thousands of photographs with high-resolution cameras, showing the far side in all stages of light and shadow. These images captured the moving Terminator line and the full sunlight shining across the far side during its lunar day. Beyond the famous Apollo missions, NASA continued to explore the Moon with a new generation of robotic travelers that revealed its secrets in astonishing detail. During the 1960s, the Lunar Orbiter program sent a series of spacecraft that carefully photographed almost every part of the Moon, including the mysterious far side that humans had never seen before. These orbiters carried powerful cameras that captured thousands of high-resolution images, showing mountains, craters and plains under many different lighting conditions, even when the far side was shining brightly in full sunlight. The photographs they sent back became the first great maps of the Moon, a vast collection of images that helped scientists study its surface and understand its ancient geology. More importantly, those early pictures clearly prove something that many people still misunderstood. The far side of the Moon is not always dark. It receives sunlight just like the side that faces Earth. Many decades later, in the year 2009, NASA launched another spacecraft called the Lunar Reconnaissance Orbiter, often shortened to LRO. Since that time, it has been tirelessly circling the Moon again and again, collecting more information than any mission before it. Its main camera, known as the Lunar Reconnaissance Orbiter Camera, or LROC, has taken millions of crystal-clear images covering every valley, mountain and crater, both on the side we see and on the hidden far side. These pictures are taken under many different kinds of sunlight, from the high midday sun that softens the shadows to the low evening sun that stretches them across the rugged landscape. All of these breathtaking images are freely available for anyone to look at, and together they show, beyond any doubt, that the far side of the Moon also glows under the golden light of the sun during its own lunar daytime. Many of LRO's maps even display the entire Moon at once, showing the moving line between day and night, called the Terminator, slowly crossing its face, providing clear visual proof that both sides of the Moon experience sunlight in turn. But LRO's discoveries go beyond just photographs. It also carries instruments that help scientists understand how sunlight affects the Moon in other ways. One of these devices is called the Diviner Lunar Radiometer Experiment. Diviner measures how hot or cold the Moon's surface becomes, and its readings have revealed dramatic changes in temperature on the far side. During the long lunar day, the surface can heat up to hundreds of degrees above 0 Fahrenheit, while during the night it drops to hundreds of degrees below zero. Such enormous swings can only happen when an area is directly warmed by the sun and then cools quickly after sunset. This pattern of heating and cooling proves that the far side experiences both day and night, just like the near side we can see from Earth. If the far side were truly trapped in darkness, its temperature would remain bitterly cold all the time, much like the deep craters near the Moon's poles that never see sunlight at all. So why do so many people still believe in the dark side of the Moon? The misunderstanding comes from mixing up two very different ideas: the side that we never see from Earth and the side that is always dark. These are not the same thing. The far side of the Moon is indeed forever hidden from our view, because the Moon turns on its axis at the same rate that it orbits Earth, always keeping one face toward us. But it is not wrapped in endless night. It has its own regular cycle of sunrise and sunset, just like the familiar near side. The only truly dark places on the Moon are found in certain deep craters near the North and South Poles. These places are called permanently shadowed regions. Their crater walls rise so high that sunlight can never reach the floor, no matter how the Moon turns. These eternally dark spots are rare and isolated, while the rest of the far side shines and sleeps under the same steady rhythm of sunlight and shadow that touches the entire lunar world. For much of the 20th century, scientists believed that the Moon was a completely dry and lifeless world, a place without a single drop of water and no geological activity. The samples that astronauts brought back during the Apollo missions of the 1960s and 1970s seemed to confirm this belief, as they showed almost no signs of moisture. Because of this, early plans for future moon bases assumed that any astronauts living there would have to bring all their water from Earth, an idea that sounded both costly and complicated. But over the past few decades, this view has changed completely. Thanks to a series of advanced robotic missions, many of them led by NASA, scientists have discovered surprising evidence that the moon actually holds traces of water, especially in its cold, shadowy craters. What was once seen as a dry, grey desert has now become a world that may contain valuable natural resources. This revelation has transformed how we think about future human exploration, making the dream of long-term lunar bases seem far more realistic. Today, searching for water ice in the moon's permanently dark craters has become one of the most important goals in modern lunar science. The hunt for water truly began to gain momentum in the 1990s. The first major clue came in the year 1994, when NASA launched the Clementine spacecraft. Clementine orbited the moon and carried a radar experiment that sent radio waves toward the polar regions and recorded the signals that bounced back to Earth. Scientists noticed that the reflected signals had strange patterns, especially in a property called the circular polarization ratio, inside some craters near the moon's south pole that never receive sunlight. These unusual reflections suggested that the radar waves might be bouncing off frozen water mixed into the soil. Though it was not absolute proof, the results from Clementine gave scientists their first strong hint that ice could be hiding in those eternally dark craters. This discovery reignited interest in the moon's poles and inspired more missions to follow. Just 4 years later, in 1998, NASA sent another spacecraft called Lunar Prospector to investigate further. This mission carried a sensitive instrument known as a neutron spectrometer, which could detect hydrogen atoms on the moon's surface. Normally, cosmic rays from space hit the moon and produce neutrons. If those neutrons collide with hydrogen, they slow down. The instrument on Lunar Prospector measured many more slow neutrons coming from the moon's polar regions, especially inside the dark, permanently shadowed craters. That meant there was a lot of hydrogen there, most likely in the form of frozen water molecules, known as H2O. Although the spectrometer could not perfectly distinguish between water ice and other hydrogen-bearing materials, the link to those dark, freezing craters made water ice the most likely explanation. This mission turned the idea of lunar ice from a hopeful theory into a strong scientific possibility. Water ice can survive on the moon because of the unique conditions near its poles. The moon's axis is tilted only about 1.5 degrees relative to its orbit around the sun, a very small tilt compared to Earth's 23.5 degrees. Because of this, the sun never rises high above the horizon at the moon's poles. Some craters there are so deep that their floors and walls never receive a single ray of sunlight. These spots, called permanently shadowed regions or PSRs, are among the coldest places in the entire solar system. Temperatures inside them can drop as low as -396 degrees Fahrenheit, or about -243 degrees Celsius. In such freezing darkness, any water that finds its way there can remain frozen for billions of years, safely trapped away from the warmth of sunlight. These places act like natural cold storage vaults, preserving the water that reaches them. Scientists believe that most of this water came from ancient comets and asteroids that struck the moon over countless ages. These icy visitors, filled with water and other frozen gases, released vapor when they hit the surface. Some of that vapor drifted across the lunar surface and eventually settled into the shadowy craters, where it froze. Another possible source of lunar water is the solar wind, the stream of charged particles constantly blowing from the sun. When these particles hit the moon, they can implant hydrogen into the soil. This hydrogen may then combine with oxygen in lunar minerals to form hydroxyl, and in some cases, actual water molecules. Over time, these molecules can also migrate to the cold traps at the poles. The final, undeniable proof that the moon truly holds water ice came in the year 2009, through a daring NASA mission called the Lunar Crater Observation and Sensing Satellite, or LCROSS. The mission was simple but brilliant. One part of the spacecraft, an empty Centaur rocket stage, was sent crashing into a large, permanently shadowed crater called Cabeus, near the moon's south pole. The other part, called the Shepherding spacecraft, followed close behind to observe what happened. On a cold October morning in 2009, the Centaur rocket struck the surface with tremendous force, throwing up a huge cloud of dust and debris. Just seconds later, the shepherding spacecraft flew through the cloud, using a set of instruments, including spectrometers and infrared cameras, to study its contents. The results were astonishing. Crust detected clear signs of both water vapor and solid ice in the plume, along with traces of hydroxyl, carbon monoxide, carbon dioxide, sodium, and even silver. The discovery revealed that the Moon's polar soil is not just frozen dust. It is a complex mix of many materials. This was the first direct, unmistakable proof that water ice exists in the Moon's dark polar craters. It completely changed our understanding of the Moon, proving that it is not a dry, dead world but a place that could someday support human life and exploration. At the same time, NASA's Lunar Reconnaissance Orbiter, or LRO, which also launched in 2009, continued mapping the Moon with extraordinary precision. One of its instruments, the Lunar Orbiter Laser Altimeter, LOLA, has created detailed three-dimensional maps of the lunar poles, helping scientists locate thousands of craters that never see sunlight. Another instrument, the Diviner Lunar Radiometer, measures surface temperatures, confirming that the permanently shadowed regions are indeed cold enough to preserve water ice for billions of years. Meanwhile, the Lunar Reconnaissance Orbiter camera, LROC, captures high-resolution images of these dark regions, using faint light reflected from Earth to reveal details hidden in the shadows. Although the cameras cannot directly see the ice itself, their images help scientists understand the harsh, frozen environments where it lies. The shape and distribution of the Moon's water ice are still being carefully studied by scientists. What they have discovered so far suggests that the ice is not found in thick, shining layers like the glaciers on Earth. Instead, it is mixed with the Moon's dusty soil and shattered rock, known as regolith. This mixture means the ice is scattered in small amounts, rather than forming large frozen sheets. In some of the Moon's permanently shadowed regions, called PSRs, places where sunlight never reaches, the ice may make up anywhere from just a few percent to as much as 1/5 of the total material by weight. Because the ice is trapped within the lunar soil, future explorers would probably need to heat the regolith to release the water as vapor, which could then be collected and turned back into liquid. Scientists are still working to calculate the total amount of water ice hidden in the Moon's polar regions, but the most recent models suggest there could be hundreds of millions of tons of it, spread across both the North and South poles. More missions and data will help refine this estimate and reveal how much of it can actually be used. The confirmed discovery of water ice on the Moon has changed everything about how humans think of space travel and future exploration. Water is one of the most valuable substances in the universe. It is essential for life itself. If astronauts can use the Moon's own water instead of carrying heavy supplies from Earth, it would make long-term missions and permanent lunar bases far more practical and affordable. The water could be used for drinking, cooking, cleaning, and even growing plants for food, turning the Moon into a far more welcoming place for humans. But the value of lunar water does not stop there. Through a process called electrolysis, water can be separated into hydrogen and oxygen. Both of these elements can serve as powerful rocket fuels, while oxygen is also vital for breathing. This means that if we can mine and process the Moon's ice, the Moon itself could become a kind of space gas station, where future spacecraft could refuel before continuing on to destinations like Mars or beyond. Such a development would dramatically reduce the cost and difficulty of deep space travel, since rockets launching from Earth would no longer need to carry all their fuel with them. This approach, known as in situ resource utilization, or ISRU, has become one of NASA's most important strategies for sustainable space exploration, and lunar water ice is at the heart of it. NASA is already planning a series of missions to study, test, and eventually use the Moon's frozen water. The Artemis program, which aims to return humans to the Moon for the first time since the 1970s, focuses on the lunar South Pole precisely because of the confirmed presence of ice there. Future robotic landers and rovers are being designed to explore these dark, frozen regions, to measure the purity of the ice, and to experiment with ways to extract and process it. The results of these missions will guide the design of future lunar bases and systems that can turn the Moon's ice into a steady source of water and fuel. NASA's long-term dream is to create a lasting human presence on the Moon, a base where people can live, work, and prepare for journeys deeper into space. Access to water ice is seen as one of the most crucial steps toward making that dream a reality. The story of the search for lunar water ice also shows how our understanding of the universe continues to grow and change. For most of the 20th century, scientists believed the moon was a dry, silent, and lifeless place, a world of dust and stone, utterly without water. But as new missions and technologies were developed, the moon slowly revealed one of its greatest secrets. It is not completely barren after all. Hidden in its coldest corners lies a treasure that could sustain future explorers and open new pathways into the cosmos. The moon does not have a wide global magnetic field like the one that surrounds Earth. On our planet, this magnetic shield is produced by a powerful dynamo deep inside its core, a region filled with swirling molten metal that behaves like a gigantic electric generator. For a long time, scientists believed that the moon's interior was too small, too cold, and too inactive to create such a process. It was thought to be a dead world, frozen solid for most of its history. But over the years, evidence gathered by NASA missions, especially those that explored the far side, has revealed surprising clues that challenge this old belief. These discoveries show that while the moon no longer has a global magnetic field, parts of its crust still hold weak, local magnetic fields, preserved like ancient fossils within the rocks. These fossil magnetic fields are silent witnesses from a distant past, offering valuable hints that the moon may once have had a lively Earth-like magnetic core. The first real proof that the moon was ever magnetic came during the Apollo missions of the 1960s and 1970s. Astronauts from Apollo 12, 15 and 16 placed special instruments called magnetometers on the lunar surface. These instruments detected faint but measurable traces of magnetism locked within the rocks where they landed. At the same time, magnetometers aboard the Apollo command and service modules, which orbited above, also detected these strange magnetic spots scattered across the surface. This was an astonishing discovery. The moon had always been seen as a small, geologically dead world, so no one expected it to have any magnetic signature at all. Yet, the evidence showed that lunar rocks carried what scientists call remnant magnetism, a leftover imprint from a time when the moon's environment was very different from today. Years later, robotic missions deepened this mystery. The Lunar Prospector mission, launched in the year 1998, carried a powerful magnetometer that made the first detailed global map of the moon's weak magnetic fields. Its data revealed that these crustal magnetic patches are found all over the surface, but they are much stronger and more frequent on the far side than on the side facing Earth. This uneven pattern became one of the great puzzles of lunar science. Even more curious, the strongest magnetic spots on the far side are located almost exactly opposite some of the moon's biggest and youngest impact basins on the near side. The presence of these strong, ancient magnetic fields suggests something profound, that long ago the moon must have had its own active magnetic core. The strength of the magnetism in certain lunar rocks is far too great to have come from external sources, such as bursts of solar wind. The only reasonable explanation is that the moon once generated its own strong planet-wide magnetic field through a powerful dynamo, much like Earth's. This changed the scientific picture of the moon completely. It was no longer seen as a cold, motionless body, but as a once vibrant world, with heat and movement deep within its metallic heart. To create a magnetic field through a dynamo, a planet or moon must meet certain conditions. It needs a core that is at least partly molten, able to conduct electricity, and moving due to heat or chemical differences. It must also rotate fast enough to keep that motion going. Early in the moon's history, billions of years ago, its small metallic core was much hotter and more fluid than it is now. Scientists still debate what kept the molten metal moving, but several ideas have been proposed. One is heat convection, where the core's internal heat drives the molten metal to rise and fall, like boiling water. Another is compositional convection, where lighter elements separate from heavier ones, creating motion. A third possibility is mechanical stirring, caused by strong tidal forces from Earth, or by the moon's own slow wobble when it orbited closer than it does today. Whatever the reason, the evidence clearly shows that conditions for a dynamo existed during the moon's early days. By studying the magnetic patterns frozen in lunar rocks, scientists have estimated when this ancient dynamo was active. The strongest traces of magnetism appear in rocks that formed between about 4.2 billion and 3.2 billion years ago. This means that the moon's magnetic engine may have run for nearly 1 billion years before it weakened and finally stopped. Younger rocks show little or no magnetism, suggesting that by then the Moon's core had cooled too much to sustain the process. When the dynamo shut down, the Moon lost its global magnetic shield, leaving its surface exposed to harsh solar winds and cosmic radiation. Over time, this exposure helps strip away what little atmosphere the Moon may once have had, leaving behind the airless, weatherless world we see today. Another mystery lies in why the strongest magnetic regions are mostly found on the far side of the Moon. Many of these areas are directly opposite or antipodal to huge impact basins on the near side, such as Mare Imbrium and the Oriental Basin. Scientists believe this is not a coincidence. According to the antipodal focusing hypothesis, when massive asteroids or comets slammed into the Moon's near side billions of years ago, they sent powerful seismic waves racing through the entire lunar body. These waves converged on the opposite side, focusing their energy like a magnifying glass. The crust on the far side would have been violently shaken, cracked, and heated. This energy could have melted or altered the rocks, and as they cooled in the presence of the Moon's strong ancient magnetic field, they became magnetized. The result was the creation of powerful local magnetic fields preserved for billions of years. Adding even more wonder to the story of the Moon's mysterious magnetism are strange surface patterns known as magnetic swirls, or lunar swirls. These are some of the most beautiful and puzzling markings found on the Moon. They appear as bright, twisting and curving streaks that seem to dance across the dark lunar surface. From a distance, they look almost as if someone had taken a pale, glowing pencil and drawn elegant spirals and loops on the Moon. What makes these swirls even more curious is that they do not match any visible landscape features like mountains, valleys or craters. They seem to float freely over the terrain, ignoring the shape of the ground beneath them. One of the most famous examples of these swirls is Rhina Gamma, located on the near side of the Moon. It shines with an unusual brightness and displays beautiful, ghost-like curves that twist across the lunar plains. Interestingly, these swirls are always found in places where the Moon's magnetic field is especially strong and unusual. Scientists call these areas magnetic anomalies. The close link between swirls and these local magnetic fields is no coincidence. Many researchers believe that these miniature magnetic fields act like tiny shields, protecting the surface from the constant bombardment of charged particles that stream from the Sun, known as the solar wind. Normally, these solar particles darken and age the Moon's surface over millions of years. But in the regions where the magnetic field is strong, they are deflected, and the surface stays lighter and less weathered. This explains why these swirls appear brighter than their surroundings. Although Rhina Gamma is found on the near side, similar, though often smaller, patterns have been discovered on the far side of the Moon as well. These two are located in areas with strong magnetic anomalies. Together, they provide striking, visible proof that the Moon's magnetism, though faint and scattered, still has a real and lasting effect on its surface. The story hidden in these magnetic traces tells scientists much about the Moon's interior and ancient history. Finding evidence that the Moon once had a global magnetic field suggests that it was once far more active than we see today. Long ago, billions of years in the past, the Moon's metallic core may have been molten and restless, generating a magnetic field through a process called a dynamo. Until recently, scientists thought such a mechanism could only exist in large worlds like Earth. But these magnetic clues prove that even a smaller body like the Moon was capable of running its own natural magnetic generator in its youth. This discovery reshapes our understanding of how planetary cores form, heat up, and eventually cool down. It means that the Moon's inner heart was once full of movement and energy, not the cold, silent shell it is today. By studying the traces of this lost magnetic field, scientists are also peering back into the Moon's thermal history, its long journey from hot to cold. The very fact that a dynamo once existed means that the Moon's interior was once extremely hot and molten. Over time, as the inner layers cooled and solidified, that magnetic generator slowly faded and stopped. The disappearance of the field marks a turning point in the Moon's life, a time when its core grew still and the heat that once flowed through its depths began to fade away. By analysing magnetic rocks and their ages, scientists can estimate how quickly the Moon lost this internal heat and how its inner layers evolved over billions of years. The pattern of magnetism scattered across the lunar crust also holds important lessons about how planetary surfaces can gain and preserve magnetic properties. One fascinating idea is that some magnetic anomalies on the far side might actually be connected to gigantic impacts that happened on the near side. In other words, a powerful collision on one side of the Moon could have rippled through its entire body, altering the magnetic properties on the other side. This shows how tightly connected a planet, or in this case, a moon, really is. Its crust and core act together, reacting to each shock or impact like a single, living system. The magnetic marks we see today are like ancient fingerprints left behind by these cosmic events. Each swirl and anomaly tells a part of a much larger story, a story of violent impacts, shifting heat, and a slowly cooling world. In its early days, when the Moon's dynamo still worked, its global magnetic field would have served as a protective shield, much like the one surrounding Earth today. It would have deflected harmful solar wind particles and cosmic rays, offering at least some defense for the surface and any fragile gases that might have formed a thin atmosphere. But when that magnetic shield eventually faded, the Moon was left exposed to the full force of space weather. Without protection, its surface was bombarded by radiation and solar particles, gradually darkening and changing its appearance. Understanding this transformation helps scientists reconstruct how the Moon's surface evolved over time and how it interacted with the harsh environment of space. The uneven spread of magnetic anomalies across the Moon's surface also reveals deep and lasting differences between the near side and the far side. These differences are not limited to what we can see, like the variations in crater density or crust thickness, but reach deep into the Moon's interior. They hint that the Moon's inner structure itself may be lopsided, with one side cooling and reacting differently to cosmic impacts than the other. To explore these mysteries, NASA and other space agencies have carried out detailed magnetic mapping of the Moon. Spacecraft such as Lunar Prospector, launched in the late 1990s, and Japan's Kaguya Selene mission, launched in the early 21st century, have carefully measured the Moon's weak but intricate magnetic fields. These missions have produced some of the most detailed maps ever made of the Moon's hidden magnetism. Future missions are expected to carry even more advanced instruments, capable of detecting the smallest variations in the Moon's magnetic field. With these high-resolution maps, scientists hope to learn exactly how these mysterious magnetic patches interact with the solar wind and how they have shaped the Moon's face over billions of years. Understanding the Moon's rocks and minerals is essential for uncovering the secrets of its birth, its long journey through time, and the hidden layers beneath its surface. Simply put, rocks are solid natural mixtures made up of one or more minerals, while minerals themselves are solid chemical substances that form naturally with a specific crystal pattern. Most of the Moon's rocks are igneous, meaning they were created when melted rock cooled and hardened. But the Moon's surface also contains large amounts of breccias, rocks made from pieces of older rocks crushed together and stuck by the strong heat and pressure of impacts. NASA's detailed lunar missions, from astronauts bringing back rock samples to advanced tools on orbiting spacecraft, have carefully mapped and identified these rocks and minerals. These efforts have allowed scientists to compare the well-known near side of the Moon with the mysterious far side, showing an amazing variety of surface features and giving deep understanding of the Moon's history and inner structure. Among the Moon's minerals, the most common and widespread is plagioclase feldspar, which forms the main part of a rock called an orthosite. An orthosite is a light-coloured, relatively low-weight igneous rock that makes up the Moon's bright, rough highlands. Scientists believe that an orthosite formed very early in the Moon's history, around 4.5 billion years ago, when the Moon was covered by a huge global ocean of melted rock, known as the Lunar Magma Ocean. As this ocean slowly cooled, the lighter minerals, including plagioclase feldspar, floated to the surface. Layer by layer they built up what became the Moon's first crust, the highlands we can still see today. The wide presence of an orthosite, especially on the far side of the Moon, stands as strong proof of this early separation into different layers: a heavy core, a middle layer called the mantle, and a lighter crust. In contrast, the Moon's darker, smoother plains, called Maria, are made mostly of a very different rock: basalt. Lunar basalts are dark, fine-grained rocks rich in iron and magnesium-containing minerals such as pyroxene and olivine, and often containing large amounts of titanium. These basalts formed from volcanic activity, when melted lava flowed into large impact basins and hardened. The presence of pyroxene and olivine is especially interesting because these minerals also exist in the Moon's mantle beneath the crust. showing that the lava of the Maria came from partly melted material deep inside the Moon. Another special and scientifically important rock type is creep, a short form for potassium, rare earth elements, and phosphorus. These elements are called incompatible because they do not easily fit into the crystal structure of common rock-forming minerals like plagioclase feldspar or pyroxene. As the lunar magma ocean hardened, these incompatible elements became gathered in the last remaining melted parts. When these creep-rich melts erupted, they produced creep basalts, which are often rich in radioactive materials that create internal heat. The uneven spread of creep rocks gives important clues about the Moon's volcanic activity and its heat changes over billions of years. The Moon's surface is also mostly made of breccias. For billions of years, asteroids and comets have hit the Moon, breaking up its surface. As a result, the Moon is mostly covered by a thick layer of regolith, a loose broken soil made up of dust, small rock pieces, and glass beads formed by impact melting. Buried within this regolith, and going deeper into the crust, are countless breccias. These rocks are like natural concrete, pieces of older rocks crushed together and joined under the huge pressures and heat of later impacts. Polymicted breccias, which contain pieces of many different rock types, are especially common in the Highlands, showing how much the lunar surface has been reshaped over time. The most direct way scientists have studied the Moon's rocks is by studying samples brought back by Apollo astronauts. Between 1969 and 1972, astronauts collected about 842 pounds, 382 kilograms, of lunar material, including rocks, soil, small stones, and core samples from 6 landing sites on the Moon's near side. These samples confirmed that an orthosite makes up the Highlands, basalt forms the Maria, and creep-rich rocks exist in certain areas. Careful lab studies of these valuable materials showed their exact chemical and isotopic makeup, helping scientists find out the Moon's age, how it separated into layers, and how it cooled over time. The Soviet lunar missions also brought back small samples from 3 spots on the near side, further adding to our direct knowledge. But these physical samples come only from a few places on the Moon, mostly the near side. To study the rest of the Moon, especially the far side which astronauts have never visited, scientists depend on remote sensing tools aboard orbiting spacecraft. These tools do not bring rocks back to Earth. Instead, they study light, heat, or radiation reflected or sent out from the Moon's surface, allowing scientists to map its mineral makeup and uncover its hidden geological secrets without ever touching the ground. One of the most important tools for finding which elements make up the Moon's surface has been the gamma-ray spectrometer, often called the GRS. This tool was carried on missions such as NASA's Lunar Prospector, which was launched in 1998. The GRS works in a fascinating way. When cosmic rays, high-energy particles from space, hit the Moon's surface, or when naturally radioactive elements like thorium, uranium, and potassium give off radiation, the GRS detects the resulting gamma rays. Each element gives off gamma rays at very specific energy levels, like a unique fingerprint, allowing scientists to make global maps showing where different elements are most common. On the far side of the Moon, the GRS found much lower amounts of iron, titanium, and thorium compared to the large dark lava plains, or Maria, on the near side. Because iron and titanium are common in volcanic rocks called basalts, this strongly suggested that the far side highlands are mostly made of anorthosite, a rock that is poor in these metals. The lower thorium levels also showed that heat-making materials, known as creep, are mostly found on the near side. This difference helps explain why the 2 sides of the Moon have very different volcanic histories. Working together with the gamma-ray spectrometer, Lunar Prospector also carried an X-ray spectrometer. This tool detected X-rays bouncing off the lunar surface when it was lit by the sun. It was especially sensitive to lighter elements like aluminum, silicon, and magnesium. The X-ray data supported the idea of the far side highlands being mostly anorthosite, showing higher levels of aluminum, a main part of plagioclase feldspar, and lower levels of iron, which matches what scientists expect from the Moon's original crust. Another amazing tool aboard Lunar Prospector was the neutron spectrometer. Cosmic rays hitting the lunar surface produce neutrons, and when these neutrons pass through hydrogen atoms, they slow down. By detecting these slower neutrons, the tool could find hydrogen. The data showed higher amounts of hydrogen, believed to be water ice, especially in permanently shadowed areas at the Moon's poles. Many of these icy cold traps are on the far side, including the giant South Pole-Aitken Basin. This discovery was groundbreaking, proving that the Moon holds a valuable resource that scientists once thought did not exist. Earlier, NASA's Clementine mission, launched in 1994, carried a multi-spectral camera that photographed the Moon in many colours of light, from visible to near-infrared. Different minerals absorb and reflect light differently, producing unique colour patterns. By studying these, Clementine helped create the first global maps showing the far side and near side highlands, made mostly of anorthositic rocks. It also showed signs of pyroxene and olivine, minerals usually found deep inside the Moon. These minerals were especially seen in large impact basins like the South Pole-Aitken Basin, showing that such massive collisions had broken through the crust and brought deep material to the surface. More recently, NASA's Lunar Reconnaissance Orbiter, or LRO, launched in 2009, has given the most detailed composition map so far. LRO carries the Diviner Lunar Radiometer experiment, which measures heat, or thermal infrared radiation from the surface. Different minerals give off heat in different ways, creating a kind of thermal fingerprint. Diviner has used these fingerprints to make detailed global maps of the Moon's main rock types, confirming the rule of feldspathic or anorthositic rocks in the highlands, and clearly showing the basaltic makeup of the Maria. It can even tell apart different kinds of silicate minerals, giving scientists a better understanding of the Moon's surface. While LRO's Lunar Reconnaissance Orbiter camera, or LROC, mainly takes high-quality visible light photos, these pictures are extremely useful. They show the Moon's surface textures, the spread of boulders and rocks, and how worn down different features are. When combined with the colour and element data, these pictures help scientists understand the rock types below and the processes that shaped them. For example, LROC images show that the highlands are often made up of broken rocks, crushed and reshaped over billions of years by constant impacts. Some of the most exciting discoveries have come from the far side, especially the huge South Pole-Aitken Basin, which covers a large part of the far side. Data from orbiting tools suggest that this basin shows rocks from deep within the Moon, including possible mantle material. Scientists have found olivine and pyroxene, minerals usually buried deep in the Moon, on the basin floor. This is very important because it shows that the spay impact was so strong that it broke through the crust, showing deep material without the need for drilling. It gives scientists a rare look into the Moon's inner layers, revealing clues about its makeup and formation. Although the far side of the Moon does not have large areas of creep-rich basalts, scientists using orbiting tools have found something interesting. They have detected small and scattered spots with higher amounts of thorium, one of the key elements found in creep. These patches are rare and small, yet they tell an interesting story. Their presence suggests that the far side of the Moon may have had very local volcanic activity, or maybe unusual surface processes that somehow brought these heat-making incompatible elements to the surface. Even though these cases are small compared to the larger patterns of lunar geology, they are very valuable because they help improve our picture of how heat once moved through the Moon's inside and how the Moon cooled and changed over billions of years. The surface of the Moon is an extremely harsh and unfriendly place for any kind of life. One of the main reasons for this is the constant and powerful bombardment of space radiation. Unlike Earth, which is protected by a strong magnetic field and a thick life-supporting atmosphere, the Moon has none of these important shields. Because of this, its whole surface is directly exposed to all kinds of cosmic and solar radiation. This exposure creates serious health dangers for any future human explorers and big challenges for the long-term use of robots or unmanned machines. NASA has spent a lot of time and resources studying this radiation in detail, especially through missions like the Lunar Reconnaissance Orbiter, often called LRO, and through the direct experiences of the Apollo astronauts. Knowing the levels of this radiation, especially on the far side of the Moon, is very important for planning any long human stay beyond low Earth orbit. Space radiation is mainly made up of two main types: galactic cosmic rays, or GCRs, and solar particle events, or SPEs. Galactic cosmic rays are extremely high-energy particles that come from outside our solar system. They are often created by violent events in faraway galaxies, such as exploding stars called supernovae. These particles are mostly atomic nuclei that have lost their electrons, including protons, helium nuclei, and heavier ions. Moving almost at the speed of light, GCRs are always present, forming a steady background of radiation that fills the entire solar system. Because of their very high energy and small size, GCRs can pass through almost anything. They can go through spacecraft walls and even through thick layers of shielding, making them very hard to stop. Long exposure to GCRs is a major concern for astronaut health on missions lasting many months or even years. Solar particle events, on the other hand, are sudden bursts of high-energy particles thrown out from the Sun. These events are often connected to powerful solar flares and coronal mass ejections, huge blasts of plasma and magnetic fields from the Sun's outer layer, called the corona. SPEs are mostly made of fast-moving protons, but they can also include electrons and heavier ions. Unlike the steady presence of GCRs, SPEs are unpredictable and can change greatly in strength. When a strong SPE happens, it can deliver dangerous, even deadly doses of radiation in a very short time. Their appearance follows the Sun's roughly 11-year activity cycle. During times of high solar activity, called solar maximum, SPEs become more common and more intense. While exposure from an SPE is short compared to the constant background of GCRs, it poses an immediate and serious danger to anyone on the Moon or in space. Earth, in contrast, has strong natural defences against these particles. Our planet's magnetic field, called the magnetosphere, pushes away most charged particles from both GCRs and SPEs, bending them around the planet. The few that do get through are mostly absorbed by Earth's thick atmosphere, which acts as a strong shield. This combination of magnetic and atmospheric protection makes Earth's surface and even low Earth orbit much safer from harmful space radiation. For example, the International Space Station, which orbits well within Earth's magnetosphere, benefits from this protection and experiences radiation levels much lower than those in deep space or on the Moon. The Moon, however, has no real atmosphere and no global magnetic field. Its entire surface is fully exposed to both GCRs and SPEs, with nothing to block, absorb or deflect these dangerous particles. NASA first began collecting direct data on lunar radiation during the Apollo missions in the 1960s and 1970s. Astronauts carried small devices called dosimeters to record how much radiation they were exposed to. These readings showed that radiation levels on the Moon, both on its surface and in orbit, were far higher than anything in Earth orbit, proving that the Moon has no natural protection. Some Apollo missions also carried special experiments, like the Apollo Passive Dosimeter Experiment, APDE, and cosmic ray telescopes, to better study the radiation. These early results were very important in showing that future missions would need strong shielding. While Apollo astronauts spent only a few days on the Moon, so their exposure to GCRs was limited, they still had to be ready for sudden solar particle events. Their training included moving quickly into the more protected command module during a strong solar storm. The most detailed and continuous radiation measurements have come from NASA's Lunar Reconnaissance Orbiter, LRO, launched in 2009. LRO carries an instrument called the Cosmic Ray Telescope for the Effects of Radiation, or CRATER. CRATER's main job is to measure radiation on and around the Moon very precisely, and to study how different shielding materials can reduce its effects. The instrument uses detectors made from plastic that mimics human tissue, allowing scientists to estimate the doses of radiation astronauts might receive. Orbiting the Moon, LRO provides full coverage, meaning CRATER measures radiation on both the near and far sides. The data clearly show that GCR levels are very high everywhere on the Moon. Measurements show that radiation levels on the Moon's surface are about 2 to 3 times higher than those on the International Space Station, proving how much harsher the environment is beyond Earth's protection. While the Moon itself blocks some particles from below, most radiation comes from above or from the sides, making work on the lunar surface very risky without strong protection. In recent years, scientists have been able to get direct radiation measurements from the far side of the Moon, thanks to China's Chang'e 4 mission. This historic mission landed its rover, Yutu-2, in the huge South Pole-Aitken Basin on the Moon's far side in January 2019. The lander carried tools designed to study radiation, including a neutron detector and a radiation sensor. The data collected were the first long-term direct readings from the far side. These measurements matched what NASA's LRO had found from orbit using CRATER, and were similar to the radiation levels recorded by Apollo astronauts on the near side. Together, these results confirm that radiation levels are mostly the same across both sides of the Moon, because it lacks a magnetic field and thick atmosphere to protect it. Understanding lunar radiation on both sides of the Moon is vital for future human missions. Galactic cosmic rays create a steady, low-level but deeply penetrating background of radiation. While not immediately deadly on short missions, long-term exposure can seriously harm health. These powerful particles can damage DNA, cells, and body tissues in ways that build up over time. Because of their very high energy, GCRs are very hard to block and need thick shielding to lessen their effect. Solar particle events are an even greater short-term danger. They happen suddenly and can release a flood of energetic particles that might give unprotected astronauts a deadly radiation dose in just a few hours. This makes strong warning systems and quick protective actions essential. When radiation from GCRs or SPEs hits the Moon's surface or a spacecraft, it can create secondary radiation, a kind of splash of new particles like neutrons and protons. This adds even more radiation to what astronauts receive, making careful habitat design even more important. The health dangers from lunar radiation are serious. Short-term effects, though unlikely on short missions unless a big SPE happens, can include radiation sickness with symptoms like nausea, vomiting, or burns that could disable astronauts. The long-term effects, especially from ongoing GCR exposure, are more troubling. These include a higher lifetime risk of cancer, damage to the nervous system that could affect thinking and lead to brain disorders, heart disease, and cataracts. GCRs are especially harmful because they include heavy ions that cause complex damage to body tissue, which the body has trouble repairing. Because of these dangers, planning for a long-term human stay on the Moon, especially on the far side, requires strong protection plans. One of the best natural shields is the lunar regolith, or surface soil. Thick layers of this soil can absorb and block radiation, making it a useful natural resource for building safe shelters. Future moon bases might be built under thick piles of regolith, inside lava tubes, or in underground structures that use this natural protection. A regolith layer several meters thick could greatly reduce exposure to both GCRs and SPEs, providing vital safety for astronauts. Besides physical shields, early warning systems are very important. Watching solar activity from Earth or from satellites can alert crews to incoming solar particle events, giving them precious time to move to safe storm shelters in their habitats. These shelters would be lined with heavy materials like water, plastic, or thick regolith to block radiation. Mission plans would include clear steps for moving quickly to safety during dangerous times. Other safety measures include keeping missions short to reduce radiation exposure, especially during active solar periods, and choosing crew members based on how sensitive they are to radiation, though this is still being studied. Scientists are also researching medicines that could help repair radiation damage or boost DNA repair, though these are still experimental. Although the Moon's lack of a magnetic field and atmosphere means radiation levels are mostly the same everywhere, there are small differences. For example, Earth's magnetotail, a long stretch of its magnetic field, sometimes sweeps across the near side of the Moon, slightly reducing the flow of solar particles for a short time. The far side, however, stays outside this small shield, facing steady cosmic and solar radiation. This difference is small overall but shows how harsh the far side's environment truly is. More importantly, if a major SPE happens while astronauts are on the far side and out of contact with Earth, they would not receive real-time warnings. This shows why local radiation monitoring and emergency systems are absolutely necessary for future moon missions.